Welcome to the Extraordinary 10 podcast, the place where the most magnificent and mind-bending facts in existence are explained to you in vivid detail.
It is great to be here. I'm excited for this one.
Today, we are embarking on a massive journey. We've researched 10 extraordinary facts about the Earth.
And we're not just, reading off a list.
No, absolutely not. We are diving deep into the science, the mystery, and the why behind these wonders.
Exactly. We're looking for those connections that turn a simple fact into a profound realization about our place in the universe.
If you love exploring the unknown, don't forget to share this deep dive with a friend and subscribe to the channel.
It really is the best way to support the show.
And it ensures you never miss a deep dive.
All right, are you ready to see the world differently?
Let's do it.
Let's start the clock. This is the Extraordinary Fact 10.
Here we go.
Welcome to the Extraordinary 10 podcast. Today, we begin our journey. Let's start the clock with fact number 10.
And this isn't just a fact. I'd argue it's the prerequisite for every other fact we could possibly talk about. We are calling fact number 10 Earth's solar energy sweet spot. But before we get into the heavy physics or the numbers, I want to try something.
Oh.
A visualization exercise.
Yeah.
Because looking at the research, it seems the only way to really appreciate where we are is to vividly experience where we aren't.
I love that.
Yeah.
Comparative planetology, looking at our neighbors, is really the only mirror we have to see ourselves clearly.
Yeah.
If you only look at Earth, you just take it all for granted.
Exactly. So I want you to imagine you are not sitting here listening to us. Imagine you are standing on the surface of a world just beyond the orbit of Mars.
Okay.
You're in a spacesuit, obviously, because there's no air. You look down at your boots. The ground is this rusty, oxidized dust. It's silent.
And not just quiet, absolute, total silence.
Right. And beneath that dust, what's under there?
You're standing on top of ancient history. There are likely vast ice deposits there. Water that might have flowed billions of years ago but is now locked away, frozen harder than granite.
It's like a planetary graveyard. So you look up at the sky. It's perpetually dim, kind of like a cloudy winter afternoon that just never ends. You search for the sun, but what do you see?
From that distance, the sun is just a pale, shrunken disk. It's bright, sure, but it feels distant. It offers barely a whisper of warmth.
Just not enough.
Not nearly enough. The energy reaching you is too diffused to drive any dynamic systems like rain or flowing rivers. It's a static, frozen world where chemistry has essentially stopped, just waiting for energy that will never come.
Okay, so that's the freezer. It's lonely, it's cold, and it's basically dead. Now let's slingshot the other way.
Inward.
We're going to fly past Earth, ignore it for a moment, and head inward toward Venus.
Now you're entering a realm that is hostile in a completely different way. As you approach, the sun looms large. It's about 1.9 times brighter than what you see on Earth.
So it's not a comforting presence.
Not at all. It's a blazing furnace.
And you can't even see the surface from space because of the clouds, right?
Right. The atmosphere is thick with sulfuric acid. If you were brave enough to stand on the surface, the atmospheric pressure would crush you like a soda can. It's 90 times the pressure of Earth. But the heat.
The heat is the real killer.
The temperature exceeds 450 degrees Celsius. That is hot enough to melt lead.
That detail always sticks with me. Hot enough to melt lead. So we have the freezer on one side where water is a rock, and the incinerator on the other where water, well, it would just instantly boil away.
And perched precariously between those two hellscapes is Earth.
This is the image I want to land on. Come back to Earth. Imagine standing on a beach at dawn, that golden light spilling across the water. You feel that warmth on your skin. It stimulates you, but it doesn't incinerate you.
And the water lapping at your feet.
It's liquid. It's not ice. It's not steam.
And that fluid reality exists for one specific reason.
Yeah.
Our cosmic address. We're exactly 149.6 million kilometers from the sun.
149.6 million kilometers. It's a number we learn in school and then immediately forget. But in the context of the universe, that number is remarkably precise, isn't it?
It's the defining metric of our biology. That specific distance allows for what physicists call the triple point of water to exist naturally on the surface. We are in the sweet spot.
And if you change that distance,
You lose the liquid water. And if you lose the liquid water, you lose the mechanism for life as we know it.
Okay, let's unpack this sweet spot concept because it sounds a lot like the Goldilocks story. Not too hot, not too cold. It sounds nice and almost like a fairy tale. But looking at the data, this isn't about luck, is it?
No, it's not magic at all. It's hard thermodynamics. When we talk about the sun, we need to stop thinking of it as a decoration and start thinking of it as a massive nuclear reactor.
Our cosmic thermostat.
Exactly.
What?
Cosmic thermostat. And that implies a very specific setting.
Okay, so what is that setting?
Well, every star has what we call a habitable zone. It's a donut-shaped band of space surrounding the star. Inside this band, the stellar radiation is strong enough to keep water liquid, but not so strong that it strips the planet's atmosphere away.
And for our solar system, that band is?
Roughly 0.95 to 1.37 AU wide.
Just to clarify for everyone listening, AU is an astronomical unit, which is the distance from Earth to the sun. So we are at exactly 1 AU.
We are the standard. The zone extends a little bit inward toward Venus and a little bit outward toward Mars. But here is where the Goldilocks analogy kind of fails.
Oh, so?
We tend to think of Earth as sitting in a big, comfortable armchair in the middle of a room. That we have plenty of space to stretch out.
Right, like if we drifted a little bit, it wouldn't be a big deal. We'd just, put on a sweater or turn on a fan.
But a better analogy, based on the climate models we have, is that we are balancing on a tightrope.
A tightrope. That implies a much higher, much more terrifying level of risk.
The margins are surprisingly thin. If you were to move Earth just 5% closer to the sun, only 5%.
That isn't much at all.
No. We would hit a tipping point. The oceans would heat up enough to put massive amounts of water vapor into the atmosphere.
And water vapor is a greenhouse gas.
A potent one. It traps heat better than almost anything else. So more heat means more vapor. More vapor traps more heat. It becomes a runaway feedback loop.
And then?
Eventually, the oceans evaporate entirely and the hydrogen escapes into space. We effectively turn into Venus.
Just 5% closer. That's terrifyingly narrow. It's like standing on the edge of a cliff and realizing your toes are hanging over.
It is. Now go the other way.
Yeah.
If you shift us about 20% farther out,
What happens then?
the planet cools. Ice sheets form at the poles. Ice is white. It has a high albedo, meaning it reflects sunlight back into space.
So the planet absorbs less heat, gets colder, makes more ice. Oh, it's another feedback loop.
Exactly. The ice advances toward the equator. Eventually, the entire planet is encased in ice. We risk becoming a snowball world where the oceans freeze over entirely and life gets choked out.
So we really are walking a razor's edge. It's not just that we are in the zone. We are navigating a very narrow path within that zone where our specific atmosphere can handle the energy load without spiraling out of control.
That's the key. It's an equilibrium.
Yeah.
There is another layer to this complexity that even people who follow astronomy often forget.
What's that?
We usually think of the habitable zone as a location in space, like a set of GPS coordinates.
Sure, distance. 149.6 million kilometers. That's the fact number 10.
But it's not just about space. It's also about time.
Time. How does time factor into where we sit in the solar system? Our orbit is stable, isn't it? We aren't spiraling into the sun.
The orbit is stable, but the light bulb is changing. The sun is not a static object. It is a main sequence star, which means it is burning hydrogen to helium in its core.
Okay.
As it does that, the core gets denser and hotter. The result is that our sun's luminosity, its brightness, increases by about 10% every billion years.
Oh, wow. So the thermostat is slowly turning itself up.
Constantly. If you go back to the Archean eon a few billion years ago,
Yeah.
the sun was much dimmer, maybe 70% of its current brightness.
Hold on. If the sun was 30% dimmer, shouldn't Earth have been a frozen block of ice? That sounds like we were way outside the sweet spot back then.
That is actually a famous problem called the faint young sun paradox. And the reason we weren't a snowball is that our early atmosphere was totally different, much thicker, likely full of methane and CO2.
Ah.
It acted like a heavy blanket to trap the meager heat that was available.
So the planet compensated for the weak sun. It wore a heavy coat because the heater wasn't working so well.
It did. But now, fast forward, the sun is getting brighter. That means the inner edge of the habitable zone, the too hot line, is moving outward. It's creeping toward us.
Wait, so the zone itself is moving and we are just staying put.
Correct. We are currently in the sweet spot, but that spot is shifting. We are living in a rare convergence where our planetary position and the sun's current brightness align perfectly for complex life.
That really changes how I look at the blue sky. It's not just a permanent fixture, it's a temporary arrangement. Which I guess brings me to the big question here. If this balance is so delicate, this tightrope walk of space and time, how rare is it?
That is the multi-billion-dollar question driving missions like the James Webb Space Telescope. We've discovered over 5,000 confirmed exoplanets now.
Which is just an explosion of discovery. I remember when we didn't know if there were any other planets.
Right, and we are learning that rocky worlds, planets physically like Earth, are actually quite abundant. The galaxy's full of rocks. But finding one at exactly the right distance from a stable star, that is the challenge.
Because if they're too close, they're fried. Too far, they're frozen.
Exactly. And even if they are in the zone, the star has to be stable. We see a lot of planets in the habitable zones of red dwarf stars, but those stars are volatile. They blast their planets with massive X-ray flares that might strip away their atmospheres entirely.
So you could be in the sweet spot for temperature, but you're getting nuked by radiation.
Precisely. Or the planet might be tidally locked, where one side always faces the star and boils, while the other side freezes in eternal night. Our sun is actually remarkably boring in stellar terms.
And that's a good thing.
That boringness is a prerequisite for life.
So we have the right rock at the right distance around the right kind of boring star at the right time in that star's life. It really feels like we hit the cosmic lottery.
Yes, and that brings us to the concept of responsibility. We talked about the sun getting brighter. In the very long term, we're talking roughly 1 billion years, the sun will be so bright that Earth's natural regulatory systems might fail.
What happens then? Does the planet just dry up?
Well, Earth has this amazing system called the carbonate-silicate cycle. Think of it as a slow-motion thermostat that regulates CO2 over millions of years to keep temperature stable.
Okay.
But as the sun brightens, this system may not be able to act fast enough to keep the planet cool. The moist greenhouse effect begins.
1 billion years is a long time, obviously. It's hard to lose sleep over it when I have to pay rent next week.
It is. But it raises a fascinating speculative question. Will humanity, or whatever life exists then, adapt? Will we migrate to the outer solar system? Maybe Mars will be the new sweet spot.
Or will we engineer a way to shade the planet with giant mirrors?
Who knows? It sounds like sci-fi, but it's a real physical deadline. The lease on Earth expires eventually.
It does. But let's connect this to the present day. Because so what? Is always the question, right? Why does knowing about the solar constant matter to you and me right now, today?
Yeah, if we have 1 billion years before the physics breaks down, why worry?
Exactly.
Because we are currently messing with the machinery. We talked about how a 5% shift closer to the sun would cook us.
Right, the runaway greenhouse effect.
Well, we can achieve that exact same overheating effect without moving the planet an inch.
You're talking about changing the atmosphere.
Yes. The sweet spot relies on a balance between energy coming in and energy going out. By pumping greenhouse gases into the atmosphere, we are trapping more energy. We are effectively mimicking the effect of moving the planet closer to the sun.
That is a very sobering thought. We are replicating a celestial catastrophe through industrial means.
We are conducting an uncontrolled experiment with the very thermostat that has kept Earth temperate for billions of years. We know the margins are thin. We know the feedback loops exist.
It really highlights that our cosmic address, as you called it, is a privilege, but it's incredibly fragile.
It is a privilege, but it's also a responsibility. We are the only species capable of understanding this balance. The dinosaurs didn't know about the solar constant. We do.
And so we're the only ones who can break it.
Or protect it.
That's a powerful way to put it. We aren't just passengers on the bus anymore. We've realized we can reach the steering wheel.
And we need to make sure we keep it on the road.
Before we wrap up Fact 10, I want to leave the listener with something to think about. We talked about the sun getting brighter in the distant future. But imagine if we found a planet that was just entering its habitable zone now.
Ooh, I like that.
A world that was frozen for billions of years and is just now thawing out because its star got brighter.
That is a beautiful thought. Just like Earth had its moment to shine, literally, other worlds might be waking up right now.
What kind of life would emerge there? It's fascinating to think that habitable zones are creating new potential Edens all across the galaxy, even as others fade away.
The universe is constantly refreshing its potential for life. And we are just lucky enough to be awake for our turn.
That was Fact 10. Stay tuned, Fact 9 is coming up next. Welcome back. We are moving right along in our countdown. Let's dive into Fact number 9.
Number 9. And, looking at the research for this one, I have to say, this is one of those topics where once you really get it, you just never look at the night sky the same way again.
I feel like we say that a lot, but this time it's about the moon. And I know what you're thinking. We all know the moon. Big, glowing rock.
Makes the tides go in and out.
Exactly. Wolves howl at it. We landed on it. We get it. It's our celestial backyard.
Right. It's maybe the most familiar thing in the universe besides the sun.
Yeah.
But the goal of this deep dive isn't to talk about, craters or Apollo flags.
The romance of it all.
No. We need to talk about the moon as a piece of heavy machinery. Specifically, the moon as a planetary stabilizer. Because without it, the research is pretty clear. Earth would be a very, very different place.
And much more hostile.
Oh, unbelievably hostile.
It's like the difference between a smooth cruise and a roller coaster that just never ends. So let's start with the thought experiment that frames this whole thing. The ultimate what if. You snap your fingers and poof, the moon is gone, vanished. What happened?
Well, the first thing, the immediate change, is the night sky.
It just goes dark.
Pitch black. I mean, you'd lose that silver glow that lights everything up. All you'd have are the stars, maybe a comet here and there.
Yeah.
It'd be this deeper, lonelier kind of darkness.
Which is sad, for sure. Bad for poetry. But, we could buy more flashlights. The real problem isn't the view, is it?
No. The real problem is the climate architecture. And I don't just mean it gets a bit colder. I mean the fundamental rules of how our planet works. They just collapse.
The Earth loses its balance.
That's the perfect way to put it. It loses its balance.
Okay, let's unpack that. Because when I think of the moon, I think gravity, I think tides. I don't really think of it holding the Earth up.
Think of it less like holding us up and more like keeping us straight.
Meh.
This brings us to a concept called obliquity.
Obliquity, that's just the fancy word for axial tilt, right?
Exactly. The angle the Earth leans at while it spins. Like a globe in a classroom isn't straight up and down. It's tilted.
Right, at about 23.4 degrees.
Precisely. And that's our whole deal. We're a very polite planet. We oscillate, but very gently. We nod back and forth, maybe between 22 and 24 degrees over a super long cycle. It's a tight, safe range.
And just to be clear, that tilt is the entire reason we have seasons.
The only reason. When the North Pole leans toward the sun, you get summer. When it leans away, you get winter. That 23.4-degree tilt gives us that lovely, predictable rhythm. Spring, summer, fall, winter.
So we have this nice, stable wobble, but the twist here, the whole point of this fact, is that the moon is the only reason that number stays at 23.4.
Correct. Without the moon, that stability vanishes. The math on this is pretty shocking. Over millions of years, Earth's tilt wouldn't just nod. It would swing wildly.
How wild.
We're talking anywhere between 0 degrees, so standing straight up, and 85 degrees.
Well, wait, 85 degrees. That's basically lying on our side.
Yeah, it is. Imagine the planet just rolling around the sun like a barrel.
Let's visualize that. Let's take that nightmare scenario, the high obliquity phase. You're tilting at 85 degrees. What does a Tuesday look like?
It wouldn't look like any Tuesday. If the North Pole is pointing almost directly at the sun, you don't just get long days like in the Arctic summer now. No, you get months of continuous baking daylight. The sun would be directly overhead at the pole, 247 for half the year.
So the Arctic literally becomes the Sahara, but a Sahara where the sun never sets.
Worse than the Sahara. At least the air cools down at night. Here, the solar radiation would be relentless. The ice caps wouldn't just melt, they'd boil off. The oceans near the poles could get catastrophically hot.
And while all that's happening, while the North Pole is frying, what's going on at the equator?
The equator, which we think of as this tropical paradise, would be in perpetual twilight. Since the poles are aimed at the sun, the equator gets almost no direct light.
It would get cold?
Frigid. You'd probably see massive ice belts forming around the middle of the planet.
So you get tropical poles and a frozen equator. That's completely backwards.
Totally backwards. And the weather systems, the storms trying to move heat from the boiling pole to the frozen equator would be, hyper hurricanes. Beyond anything we can imagine.
And that's just one extreme. A few million years later, the tilt swings back to 0.
Right, 0 degrees, no tilt at all. The Earth stands straight up.
Which sounds, stable.
It's stable, but it's stagnant. At 0 degrees, seasons just stop. They don't exist. Every day, everywhere is exactly the same. The poles would freeze solid forever, and the equator would just cook under a relentless stationary sun.
It's pure chaos. It's not just that it's bad, it's that it's always changing.
That's the key. Climatic anarchy. Ice sheets wouldn't advance over millennia. They can potentially advance and retreat across just a few centuries.
How could complex life ever keep up with that? Evolution is slow. This is climatic whiplash.
It's very, very hard to imagine a civilization arising in a world like that. Just as a species adapts to an ice belt on the equator, the planet tilts, the ice melts, and the equator becomes a desert.
So enter the hero, the moon. That gray, cratered rock. How does a rock so far away stop an entire planet from tipping over?
It acts as a stabilizing gyroscope.
I love that image. But let's break down the physics. The source uses a great analogy I want to walk through. The spinning top.
Yes, everyone's spun a top. When it's going fast, it's steady. But as it slows down, what happens?
It starts to wobble. It does that little drunk circle right before it falls.
That drunk little circle is called precession. And Earth is that top. It's spinning. But here's the catch. We're not spinning in a gravitational vacuum. We've got bullies in the neighborhood.
I'm guessing Jupiter.
Jupiter's the big one. But the other planets, too, they're all constantly tugging on Earth. It's a phenomenon called planetary resonance. It's like pushing a kid on a swing. If you time your pushes just right, the swing goes higher and higher.
So Jupiter's trying to push your swing.
Exactly. Jupiter and the others are tugging on our tilt, saying, hey, lean over here. Over millions of years, those rhythmic tugs would add up. They'd amplify that wobble until the top Earth just spun out of control.
But we have the moon.
We have the moon. And the key is that our moon is big. Relative to Earth, it's huge compared to most other moons in the solar system. And because it's so big and so close, its gravitational grip is massive.
The source called this tidal torque?
Right. It applies force to Earth's shape.
Earth's shape. We're not a perfect sphere, are we?
No, we're an oblate spheroid. Because we spin, we have this little bit of a spare tire around the middle, an equatorial bulge.
Okay, a bulge?
And the moon's gravity grabs onto that bulge. It's like a giant handle. By pulling on it, the moon forces Earth's axis to precess, to do that wobble much faster than it normally would.
It speeds up the wobble.
It speeds up the precession, yes. And by speeding it up, it breaks that resonance with Jupiter. It throws off the timing of the pushes on the swing. It basically keeps us out of sync with the bullies.
It's like a steady hand on the spinning top.
A very steady hand saying, nope, you stay right here around 23 degrees. I got you.
I like the other analogy too, the bicycle wheel.
Oh, that's a classic. If you spin a bike wheel really fast and try to twist it,
It fights you. It wants to stay put.
that's angular momentum. The Earth-Moon system has so much combined angular momentum that the tugs from Jupiter just aren't strong enough to knock us off balance.
It's a cosmic shock absorber.
A gravitational anchor.
Okay.
It anchors our geometry in space.
Which brings us to the how did we get so lucky part, because like you said, a moon this big is weird.
Extremely rare. It goes back to our origin story. The leading theory is that a Mars-sized object, Theia, slammed into the proto-Earth about 4.5 billion years ago.
A violent beginning.
Incredibly violent. But the debris from that collision coalesced and formed the moon. So in a way, our stabilizer was born from utter chaos.
That is poetic. But here's the heartbreaking part from the reading, this partnership. It's not forever. It's drifting apart.
It is. The moon is leaving us.
I hate this. How fast is it going?
About 3.8 centimeters per year.
Which, the source said, is about the rate your fingernails grow. That's such a weirdly intimate comparison.
It is, isn't it? It's slow, but it's relentless.
So as it moves away, its grip on us gets weaker.
Exactly. Gravity weakens with distance. So hundreds of millions of years from now, that steady hand won't be as strong. Jupiter will start to win the tug-of-war again.
The wobble returns.
The stability will degrade, yes, but that is deep, deep time. For the entire history of humanity, we've been in the absolute sweet spot.
Which leads us to the big question. Was the moon necessary for life? Could we be here without it?
It's a big debate, but if you look at the role of the seasons, you start to see how critical that stability is.
Explain that connection. Why do stable seasons matter so much?
Well, think about migration, breeding cycles, agriculture. Life on Earth runs on predictable rhythms. Birds know when to fly south because the seasons are reliable.
Plants know when to flower.
Exactly. If you had that chaotic tilt, where one century is tropical and the next is an ice age, could complex food webs ever really develop?
It seems like life would just constantly be hitting a reset button.
That's the argument. It's part of the rare Earth hypothesis. The idea that while simple life might be common, complex, intelligent life might be exceedingly rare because you need this lucky setup. You need a big moon.
But the source does mention counter-arguments.
True. Life is incredibly adaptable. Maybe on a moonless world, life would just be tougher, more nomadic. Maybe it would learn to go dormant for centuries.
So you get super hardy organisms, but maybe not a civilization that builds libraries and podcasts?
That's the idea. Civilization needs calm. It's hard to develop agriculture if a glacier might bulldoze your farm in 200 years because the planet tipped over. You need a stable stage.
And speaking of civilization, the source mentioned the cultural impact. It's not just physics.
Oh, absolutely. The moon gave us our first calendars. The word month literally comes from moon. The tides allowed for coastal navigation, for intertidal ecosystems. We are culturally tied to that rock.
Okay, let's look to the future. Because the reading makes a prediction about where this all ends up, and it's kind of mind-bending.
The long future.
Yeah.
Yes. So we know the moon is moving away. As it does, Earth's rotation is actually slowing down. The tides create friction, acting like a brake.
So our days are getting longer.
Very, very slowly. A few milliseconds a century, but project that out billions of years, and you reach a state called tidal locking.
Like the moon is with us now, we only ever see one side of it?
Correct. The moon is locked to Earth. But eventually, Earth could become tidally locked to the moon.
What's that even look like?
It means an Earth day would last about 47 of our current days.
Wait, a 47-day?
Yes. Weeks of continuous sun baking the surface, followed by weeks of freezing night. But the stranger part is the moon itself. It would stop moving across the sky.
He would just hang there.
If you lived on the side of Earth facing it, yes, it would be a permanent fixture in one spot. A giant, unmoving chandelier.
And if you lived on the other side?
You would never see the moon, ever.
Yeah, that is haunting. A permanent fixture in the sky.
It would fundamentally change everything. But again, we're talking about a future so distant the sun itself will have changed dramatically by then.
It really emphasizes that we're living in a Goldilocks moment. Not just in space, but in time.
That's the big takeaway. For now, the moon is at the perfect distance to stabilize our axis and create strong, but not destructive tides. It's an ephemeral partnership.
But for this brief cosmic moment, it worked.
It worked. It provided the stable stage. I think that's the best way to put it. The moon built the stage so the drama of evolution could play out without the theater collapsing.
I love that, the stable stage. Makes me want to go outside tonight and just give the moon a little nod. Thanks for holding us steady.
Thanks for the seasons.
Thanks for not letting the North Pole fry.
Exactly. Thanks for handling the bullies.
So to recap fact number 9, the moon is not a nightlight. It's a planetary gyroscope. It prevents climate chaos, it gives us seasons, it's drifting away at the speed of a fingernail, and without it, we might not be here.
That sums it up perfectly. The silent partner in our existence.
It's a lot to take in, the idea that our entire world hangs on this invisible gravitational thread.
It really changes what we should look for in other worlds. When we hunt for Earth 2.0, maybe we need to be looking for a Moon 2.0 as well.
A big stabilizing moon.
Precisely. Otherwise, that planet might be a chaotic, wobbling mess.
Well, I'm going to be thinking about that 85-degree tilt all day. Terrifying stuff.
Just be glad we have our gyroscope.
I am. And as you look up at that tidally locked face of the moon tonight, remember? It's staring back, holding the line against the chaos of the cosmos. That covers 9. Ready for the next one? Let's head to fact 8.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 8.
It's good to be back, and this one, this is a subject that really messes with your sense of perspective. It forces you to look at the ground you walk on and the air you breathe a little differently.
Absolutely. So the headline for this deep dive is Earth's immense, largely uncatalogued biosphere. Now, I want to start by challenging that premise a little.
Oh, okay.
Because if I pull up my phone right now, I can load Google Earth. I can zoom in on a random street in Tokyo or a dirt road in Namibia. I mean, I can see the shingles on my own roof. It feels like we have this planet mapped down to the inch.
We do, but that's the geography. We've mapped the geography. We know where the continents end, where the shelf drops off. We know the elevation of every mountain range.
All right.
But that's a map of rock and water. If you try to layer a biological map on top of that, a map of who actually lives here, it's mostly blank.
So that's the disconnect. We're advanced enough to fly a helicopter on Mars, but the claim here is that we're basically squatters in a house filled with strangers.
That's a great way to put it. We don't even know the names of most of our roommates.
And it's not just that we haven't named them, it's that we don't even know they exist.
Exactly. I mean, despite centuries of biology, zoos, museums, all the David Attenborough documentaries, the scientific consensus is that we have observed, named, and cataloged less than 20% of the life on this planet.
Less than 20%. So 4 out of 5 species on Earth are total ghosts to us.
Correct. And that's a conservative estimate, really. Some models suggest the gap is even wider. It's like we're walking through a very crowded room wearing a blindfold.
All right, so let's try to take that blindfold off, at least in our minds. The source material uses this really effective visualization, and it starts in Borneo.
Right, one of the great biodiversity hotspots.
So picture yourself trekking through a remote rainforest there. It's not a comfortable walk. The humidity is like 98%. Your glasses are fogging up. The air is just thick and loud.
A wall of green.
Yeah.
And the assumption is that the green is just scenery, background noise.
Exactly. We see tree or bush, but not the specifics. So you look down and you see a beetle crawling over a root. The text describes it with these iridescent wing cases, catching a bit of sunlight.
And that beetle, that one specific beetle, almost certainly has no scientific name.
Which seems crazy. I mean, it's a beetle. They're everywhere.
They are, and that's the problem. The beetle order Coleoptera is just absurdly diverse. There's this famous quote from the biologist J.B.S. Haldane that the creator must have had an inordinate fondness for beetles.
Right.
There are millions of species. So unless a specialist in that specific family has walked that specific trail and collected that specific specimen, it stays unknown.
Okay, so we step over the anonymous beetle. Next to the path, there's a rotting log.
Which is like a metropolis for fungi in a rainforest.
And you see mushrooms sprouting out of it. Neon purples, vibrant oranges, they look like coral. And again, the source says, genus undetermined.
Fungi are so understudied. We know the ones we eat and the ones that can kill us, but the vast majority of them, their life cycles, their purpose, it's a mystery. They're the chemical engineers of the forest, and we barely know their names.
And then the visualization tells you to look up into the canopy.
Which is where it gets really tricky. You could be looking right at an insect and just not see it.
Because of the camouflage.
The camouflage is so advanced, they mimic not just the color of a leaf, but the veins, the texture, even the little brown spots on a dying leaf.
So even a trained biologist standing right there would miss it.
Oh, absolutely would miss it. So in a 10-minute walk, you've passed 3-4 distinct genetic lineages that science is completely unaware of, and that's on land, where it's relatively easy for us to go.
Right, and that's where the source shifts gears and takes us somewhere humans really can't go without, $1 billion of hardware. The deep ocean.
The abyssal plains, the hydrothermal vents.
This place always fascinates me because it breaks the rules we learn in school. Sun is the battery for Earth. Plants eat sun, animals eat plant.
That's the surface rule. But down there, kilometers deep, there's zero sunlight. The pressure is, imagine an elephant standing on your thumb. And it's near freezing, except right around these vents where the water is hot enough to melt lead.
And yet it's not a desert.
It's teeming. We send down these ROVs, these remotely operated vehicles, and we find giant tube worms, ghostly white crabs, eyeless shrimp.
And their whole food web, it isn't based on the sun at all.
Not at all. It's based on chemosynthesis. Bacteria down there literally eat chemicals spewing from the Earth's crust hydrogen sulfide, methane. The tube worms then farm those bacteria inside their own bodies.
It's an alien planet hosted on our own.
It really is. And because it's so hard to get to, every time we dive to a new vent system, we find something new. A new species of snail, a new type of worm. We are just scratching the surface at the bottom of the ocean.
So we have the jungle, which is too dense to catalog. The deep ocean, too expensive. But the part of this that really got me was the third location. Because it's not exotic at all. It's right under our feet.
The soil.
The dirt, the stuff we pave over.
We have this cognitive bias against it. We treat it like it's just inert matter that plants sit in. But biologically, soil is maybe the most complex ecosystem on the planet.
The source dropped a statistic here I had to read twice. A single handful of rich soil contains more microbial diversity than all the mammals combined.
It's more than that even. The genetic diversity in that handful of soil likely exceeds the genetic diversity of a whole coral reef. You've got nematodes, tardigrades, fungi, billions of bacteria. It's a war zone and a nursery all in one.
But the kicker is, the source says we've only characterized maybe 1% of bacterial species. How is that possible? We've had microscopes for centuries.
It's something called the Great Plate Count Anomaly.
But what now?
The Great Plate Count Anomaly. So, historically, to study a bacterium, you had to grow it in a lab on a petri dish. But the problem is, about 99% of soil bacteria are, let's call them fussy eaters.
They don't like the lab food.
They refuse to grow on a petri dish. They need the specific neighbors, the specific chemistry of the soil to survive. So for a century, we just couldn't see them because we couldn't grow them. They were the dark matter of the biological world.
That explains the gap. They were there the whole time, cycling nutrients, but totally invisible to our tools.
Exactly. So you combine the rainforest, the deep oceans, and the microscopic world of the soil, and the numbers just get staggering.
Let's talk about the numbers. What's the best estimate for the size of this gap?
Okay, so if we focus just on eukaryotes, that's complex life, plants, animals, fungi, the most widely cited estimate is about 8.7 million species.
8.7 million. And how many have we actually named?
Somewhere between 1.2 and 1.5 million have been described.
So we're missing roughly 85% of the picture.
At least. And this brings us to that central analogy in the source material, which I think is just brilliant, the global library.
I love this. It makes the scale manageable. So Earth is a library with 8.7 million books. Each book is a unique species.
A unique story of evolution. Right. So you walk into this library, what's the state of our reading?
Well, we've walked down the aisles and scanned the titles of maybe 1.5 million books. That's the cataloging part.
Right. But giving something a name is just reading the title on the spine. It doesn't mean you know the plot.
And the source says the number of species we've actually studied, understood their life cycle, their role, is tiny.
It's estimated at around 250,000. So in our library of 8.7 million books, we've read and understood about 3%.
That is humbling. It makes our claims of dominating the planet seem a little premature.
It means that about 6.5 million volumes are just sitting on shelves in locked wings of the library. We haven't even turned the lights on in those rooms.
And those locked wings are the places we just talked about. The deep ocean, the subterranean caves, the dark shelves.
And some shelves aren't dark, they're just overcrowded. The rainforests and coral reefs, it's like a section where the books are crammed in 10 deep. You pull one out and realize there are 50 more behind it you've never even seen.
But there's another layer here that's a bit stressful. A library is usually static. The book will be there tomorrow. The biosphere isn't like that.
No, the library is on fire.
That's a stark image.
But it's the reality. We are losing volumes before we even open them. That's the extinction crisis. We are burning books before we've even cataloged the title.
But new books are being written, right? Evolution doesn't stop.
It doesn't, but the rate of writing is so much slower than the rate of burning right now. Evolution takes millennia. Extinction can happen in a decade. The library is shrinking.
Which brings us to the big so what question. I can hear someone listening and thinking, okay, so we haven't named a beetle in Borneo. Why does that matter to me?
It's the classic question, and I think there are two answers. There's the utilitarian argument, what's in it for us, and then there's the systemic argument.
Let's start with what's in it for us.
Okay, think about your medicine cabinet. So many of our pharmaceuticals come from natural compounds. Aspirin from willow bark, penicillin from a mold, morphine from poppies.
Even modern drugs. There's a diabetes drug from the venom of a Gila monster.
Exactly, and the HIV drug AZT comes from a sponge on a coral reef. Nature is the world's greatest chemist. Evolution has spent 4 billion years running trial and error experiments.
So those 6.5 million unread books,
Yeah.
they're full of chemical formulas we haven't discovered yet.
There are potential cures for cancer, new antibiotics, new materials. When a species goes extinct before we study it, we're not just losing a bug, we're losing a potential breakthrough. We are shredding a lottery ticket without checking the numbers.
That's a very concrete risk. What about the systemic argument? This is ecosystem services, right?
Right, it sounds like a corporate buzzword, but it's vital. These are the things nature does for free: pollination, water filtration, climate regulation.
And the source put a price tag on that. Trillions of dollars a year.
It's effectively priceless. We can't replicate it. But here's the danger of the unknown part. We are pulling threads out of a tapestry, but we don't know which threads are holding the whole thing up.
The keystone species idea.
Exactly. You might think some random fungus in the soil is irrelevant, but maybe that fungus is the only thing that lets a certain tree absorb nitrogen. You kill the fungus, the forest dies, the watershed collapses, and suddenly a city downstream has no clean water.
And because we don't know the players, we can't predict the collapse.
We are flying blind. We are conducting a massive, uncontrolled experiment on the planet, and we don't even know all the variables.
It feels overwhelming. The scale of ignorance is vast and the stakes are high. But the source does talk about a new era of discovery. Some hope.
Yes, absolutely. The days of the Victorian gentleman with a butterfly net are kind of over. We're in the age of high-tech discovery now.
Two things stood out: eDNA and AI. Let's start with the DNA. Environmental DNA. How did that change things?
Think of it like forensic science. An animal is constantly shedding skin cells, hair, mucus. So scientists can now just take a cup of river water, sequence all the DNA floating in it.
And that tells you everything that lives upstream.
In theory, yes. You can detect a rare salamander without ever seeing it. You can map the biodiversity of an entire reef just by sampling the water. It scales up discovery exponentially.
But there's a catch, isn't there? If you find a DNA sequence, but you don't have a known species to match it to in your database.
That's the bottleneck. We have the fingerprints, but we don't have enough mugshots to match them to. We know something is there, but we might not know what it is.
And that's where AI comes in.
Right. AI is solving the time problem. Identifying species traditionally takes a human expert years of training. It's slow, tedious work.
And there aren't enough of those experts to go around.
But an AI can now identify a species from a photo, or a bird call from an audio file, or a genetic sequence faster than any human. It can spot patterns we can't.
So we're automating the librarian.
In a way, yes. The goal, according to the source, is that these technologies could potentially document most complex life on Earth within a century.
Within a century. That sounds fast, but with the extinction rate, it might be a photo finish.
It's a race, but it also signals a shift in ethics. In the past, discovery meant collection. You shot the bird and put it in a museum drawer.
Science by killing.
Now the shift is from collecting to understanding. We're moving to non-invasive monitoring, and the question becomes, do we need to name every single beetle to value it? Or is it enough to know the complex web exists and focus on protecting the library itself?
That's a deep question. Is the value in the catalog or in preserving the building?
I think we're realizing we'll never finish the catalog in time, so we have to become better custodians of the building, even the rooms we've never been in.
It reframes our whole role, doesn't it? We're not just consumers. We should be. Librarians.
Librarians in a library we didn't write, that we're only just learning to read.
That's a great image. So as we wrap this up, what's the one thing about this unknown biosphere that really sticks with you personally?
For me, it's the concept of the silence.
The silence.
Think about the soil again, or the ocean floor. There are billions of interactions happening every second. Creatures hunting, hiding, mating, signaling each other. It's a cacophony of life.
But to us.
To us, it's silent. We walk over it and hear nothing. We look at the ocean and it seems quiet. It reminds me that the human experience, what we see and hear and know, is just this tiny, tiny slice of the reality of Earth. We live in a bubble of our own perception.
We're the tourists walking through the city with noise-canceling headphones on.
Exactly. And just acknowledging that fact, that the silence is actually filled with millions of stories we don't know, that's the first step to truly being an inhabitant of this planet, not just a user of it.
That's profound. It definitely makes you want to walk a little softer when you go outside.
Or what's stepping on you, microscopically speaking.
I could have done without that reminder. But seriously, this has been a fascinating look at fact number 8. It's strange to classify the unknown as a fact, but the magnitude of what we don't know is maybe the most solid fact we have.
It is. It's the boundary condition of our science. It defines the edge of the map.
And it sets the stage for what's left to do. A lot of books left to read.
And a lot of shelves to unlock. You know, just to leave you with one final thought, we talked about this tapestry of life. We're just one thread. Our responsibility isn't just to understand the pattern, but to preserve it while we are still learning how to read it.
That covers 8. Ready for the next one? Let's head to fact 7. Welcome back. We are moving right along in our countdown. Let's dive into fact number 7.
This is a significant one. I'd argue this is the fact that fundamentally changes how you perceive the physical reality of the planet.
How so?
Well, it stops being just a setting for the story of life, and it starts being a character in the story.
I like that. A character. Usually when we talk about what makes Earth special, which is, the whole point of this countdown,
Right.
we have a tendency to look up.
Right.
We talk about the atmosphere, the magnetosphere, the sky, or we look out at the oceans. We look at all the biology running around on the surface.
Well, we focus on the wallpaper and the furniture, basically. The external features that are easy to see.
But fact number 7 takes us down, way
Yeah.
down. It's about what is happening underneath our feet right now. Specifically, we are talking about Earth's internal heat engine and plate tectonics. And I want to be clear about the mission for this deep dive. We need to understand how this engine works, why it sets us apart from our neighbors like Mars or Venus, and and this was the part that really surprised me. Our very existence actually depends on the ground moving.
It's not an exaggeration at all. Without this engine, Earth would be a very different and likely a very dead place.
We just think of it as a solid rock.
We do. It's easy to intuitively think of the Earth as this, solid ball that we just happen to live on, a passive stage. But the reality is, we're living on top of a machine, a massive, active churning engine.
And it is pumping out a staggering amount of energy. The source material mentions a specific number here that we really need to wrap our heads around. 47 terawatts of power.
47 terawatts. It's a hard number to even visualize.
Well, the notes give a comparison that helps. Think about all of humanity's energy consumption.
Okay.
Every power plant, every car, every light bulb, every single factory on Earth. If you add all of that up, this geological engine is producing roughly 10,000 times that amount.
10,000 times. It's the constant hum of the planet. And unlike our power plants, which we can turn off, this engine, it has been running without a break for 4.5 billion years.
That is just humbling. We are basically ants walking across the casing of a massive generator and thinking the ground is just dirt.
Exactly. We're standing on what the source calls the thin, mobile skin of a heat engine. And unlike a car engine that just spins wheels, this engine is constantly rebuilding the car while it's driving.
It destroys the old surface and creates a new one.
Precisely.
Okay, to really get a handle on this, we need to visualize it. We can't just talk about terawatts in the abstract. The source material takes us to two very specific locations to see this engine in action. I want to start with the first one. We're going to Iceland.
A fantastic place to start. Geologically speaking, it's one of the youngest places on Earth. And specifically, we're going to a place called Singalier.
So paint the picture for us. You are standing there in Iceland. It's cold, the wind is blowing, it's very stark. But you are looking at something geologically mind-bending.
You really are.
You're standing in a valley, but it's not a valley carved by a river. It's a place where the ground is literally tearing itself apart.
And that's not a metaphor. At Singalier, you are standing directly on the Mid-Atlantic Ridge. This is the boundary between the North American tectonic plate and the Eurasian tectonic plate.
And they're pulling apart, diverging.
Correct. They are moving away from each other. Now, it's slow to the human eye about the speed your fingernails grow, but in geological time, that is a dead sprint.
So you can actually stand between them.
You can physically walk between the rift. You are walking in the gap between continents.
That is wild. But here's the question I had when reading the notes. If the ground is ripping open, why isn't there just a giant hole down to the core? Why aren't we looking into this, abyss?
Because the Earth abhors a vacuum. This is where the engine part really comes in. As those plates separate, the pressure is released on the mantle below. That hot rock wells up, melts because of the pressure drop, and it fills the void.
And hardens into new rock.
It cools and solidifies to create new crust. It's essentially a crust factory.
A crust factory, I like that.
It's constantly paving the ocean floor with fresh rock. And you can see the energy of that factory at the surface. The sources describe geothermal springs just bubbling and hissing nearby. That water isn't boiling because of the weather. It's heated by magma chambers deep, deep below. The heat engine is venting right there.
So on one side of the world, in Iceland, we have the Earth making new crust, ripping apart and filling the gap.
Right.
But this leads to a logical problem. If we're making new crust and the Earth isn't getting bigger, it's not inflating like a balloon,
Right.
we have to be losing crust somewhere else.
Conservation of mass. You can't just keep printing new land without destroying the old land. And that brings us to our second location. We need to travel to the other side of the planet, to the Pacific Ring of Fire, let's say off the coast of Japan.
This is the flip side of the coin.
It is. In Iceland, we saw divergence creation. Here, off the coast of Japan, we were seeing subduction. We're seeing destruction.
Subduction. Okay, that's a term we hear in geology class and promptly forget. Let's break it down. What are we actually looking at if we could, drain the ocean?
Picture the floor of the Pacific Ocean. It's a massive slab of cold, dense rock. We call it the oceanic lithosphere. It's been traveling across the planet for millions of years, cooling down, getting heavier.
And it crashes into Japan.
It crashes into the continental crust of Japan, but it's not like two cars hitting head-on.
No!
No, because the densities are completely different. The oceanic plate is heavy. The continental plate is, relatively speaking, lighter. So the heavy oceanic plate dives. It plunges beneath the continent.
And the scale of this.
The source says we are talking about a slab of rock the size of India, slowly, relentlessly descending into the Earth's mantle.
That is terrifying. A slab of rock the size of India just sinking into the depths. And the sources emphasize that this isn't a smooth ride. It's not like it's a greased slide.
Not at all. It's rock grinding against rock under billions of tons of pressure. It sticks, it slips, it ruptures. That descent generates massive friction. This is what creates those mega-thrust earthquakes that can devastatingly shake entire countries.
So when you feel an earthquake like that, you are feeling the engine slip a gear.
That's a great way to put it, yes. And it's also fueling the volcanoes. You see Mount Fuji sitting there. That's connected.
Oh, directly connected. As that slab dives down, it gets incredibly hot. It releases fluids, mostly water, into the hot rock above it that causes melting, and magma rises to the surface to form volcanoes.
Yeah.
So when you look at Mount Fuji, you're basically looking at the exhaust pipe of the subduction zone.
So earthquake or volcano, what we are actually witnessing is the skin of the planet moving. That phrase from the source material is so evocative. The thin, mobile skin.
It really changes how you feel about the ground. It's not a foundation. It's a conveyor belt.
Powered by that 47 terawatts of heat.
Okay, so we have the visual. We have the ripping apart in Iceland, the sinking down off the coast of Japan.
Yeah.
But I want to get into the mechanics. How does this actually work? Because the source material uses an analogy here that I think is really helpful, but I need you to help me unpack it. It calls Earth a gigantic slow cooker.
It's a great analogy. Imagine a slow cooker that has been left on high since the solar system formed.
Okay, I'm picturing a crock pot. But, the slow cooker plugs into the wall. Earth doesn't have a cord. Where is the heat coming from?
Earth has two main internal power sources. The first one is what we call primordial heat.
Primordial, that means ancient.
Very ancient. Go back 4.5 billion years to when the Earth was forming. It wasn't built gently. It was built by rocky debris, asteroids, and planetesimals smashing together in space at thousands of miles an hour.
So kinetic energy converted to heat. Like clapped your hands really hard, but on a planetary scale.
Exactly. The entire planet was molten, and rock is actually a very good insulator. Think of how a pizza stone holds heat. So deep inside the Earth, we still have the residual warmth, the glowing embers from those original collisions.
Like the heat in a campfire's ashes the morning after.
But this campfire was the size of a planet.
Okay, so that's source one. Leftover heat from the construction site. It's basically a thermal battery that's slowly draining. What's source two?
Source two is radioactive decay.
The nuclear option.
In a way, the Earth's mantle and crust contain radioactive elements, uranium, thorium, potassium, and these act like nature's fuel pellets. As these atoms decay, they release tiny amounts of energy as heat.
But when you have trillions of tons of rock doing this over billions of years...
It generates immense heat. It's a slow, steady burn, keeping the stew hot.
So we have the heat source, the primordial embers, and the radioactive fuel pellets. Now let's look inside the pot. What does this do? This is where I struggle a bit with the physics. We are told the mantle is solid rock, right?
Correct. It is solid peridotite rock.
But we are also told it flows. How can solid rock flow? I think of lava as liquid, like soup. But the mantle isn't lava. If I punch a rock, it hurts. Doesn't splash.
This is the most common misconception. The mantle is not liquid. It's a thick, viscous solid. The source describes it as extremely slow-moving taffy.
Taffy.
Or think of a glacier. Ice is solid, you can walk on it. If you hit it with a hammer, it shatters. But if you look at a glacier over a year, it flows down the valley.
So it's all about the time scale.
Precisely. Under high pressure and temperature, solid rock can deform and flow, but creepingly slowly. We're talking centimeters per year. And because it's heated from below by the core, it convects.
Convection. Okay, that's the same physics as boiling water in my kitchen. Hot stuff goes up, cold stuff goes down.
Exactly the same principle.
Right.
The hot rock near the core becomes slightly less dense, a bit more buoyant. It rises slowly toward the surface. When it gets near the crust, it spreads out, cools down, becomes denser, and sinks back down. It's a huge, slow cycle.
So this giant slow cooker full of rock taffy is just churning, slowly but surely. And what about the lid? The crust we live on.
That's the lithosphere. But unlike a normal pot lid, Earth's lid is broken. It's cracked into about a dozen major pieces, and we call those pieces tectonic plates.
And these pieces are just riding on top of the churning taffy.
That's the best way to think about it. They are surfing. Where the stew wells up like in Iceland, the plates get pushed apart.
And where it goes down.
Where the convection current turns downward like off the coast of Japan, the old cold lid gets dragged back down into the stew to be melted and recycled.
Recycled, that is the key word. The source mentions a specific timeline for this recycling that really surprised me. It says the ocean floor is relatively young.
Yes, this process recycles the entire oceanic lid roughly every 200 million years.
Wait, hold on. We have rocks on continents that are billions of years old. But the ocean floor, none of it is older than 200 million years.
Generally speaking, no. The continents are made of lighter rock granite mostly, so they float like styrofoam. They don't subduct easily. But the heavy ocean floor, it's constantly being made fresh in places like Iceland and destroyed in places like Japan. The planet is literally shedding its skin and growing a new one over and over again.
Wow, that creates an incredibly dynamic surface.
Yeah.
But this brings us to the big why. Why does this all matter? To understand why this is special, the source material compares us to our neighbors. Because Earth isn't the only rock in the neighborhood.
No, we have Venus and Mars right next door, and they're made of basically the same stuff. They formed at the same time, but neither of them has plate tectonics.
Let's look at Venus first. It's almost the same size as Earth. Why isn't its lid moving?
Venus has what we call a stagnant lid. Its crust is one solid, unbroken shell. It doesn't move, it doesn't recycle. The heat just builds up underneath until, and this is a theory, the whole surface might melt catastrophically in a resurfacing event, but it doesn't have that steady conveyor belt motion that Earth has.
And Mars?
Mars is the opposite problem. It's too small. It lost its internal heat much, much faster. The engine turned off a long time ago. The lid just froze in place.
So Earth is the Goldilocks here. Not too stagnant, not too frozen. Just right. But why? Why did we get lucky?
That is one of the biggest questions in planetary science. A leading theory, though, involves water.
Water? What does water have to do with rocks moving? I thought water was just on the surface.
It turns out water is a fantastic lubricant for rock. Remember the subduction we talked about? When that plate dives down, it brings ocean water with it deep into the mantle. That water softens the rock, lowers its melting point, and weakens the crust enough to let it break and bend.
So a dry Earth might have a stuck lid like Venus.
It's very possible.
That is a fascinating connection. The oceans might actually be the reason the continents can move. But let's get to the so what. Why should we care that the plates are moving? I mean, aside from the earthquakes, which are scary, and the volcanoes, which are dangerous, is this actually a good thing for us?
It is absolutely crucial. In fact, I would argue you wouldn't be here without it. Plate tectonics is the planet's life support system.
How so? Is it just about making cool mountains?
It's about the thermostat, specifically the silicate carbonate cycle. We talk a lot about carbon dioxide in the atmosphere today, usually as a bad thing because we're adding too much. But over billions of years, Earth needs a way to regulate its temperature so liquid water can exist.
Right. If we get too cold, we freeze like Mars. Too hot, we boil like Venus.
Exactly. Plate tectonics manages this balance. Volcanoes, which are caused by the plates moving release carbon dioxide, that acts as a greenhouse gas to keep the planet warm.
Okay, so volcanoes turn up the heat.
But if you just keep pumping CO2 out, you end up like a runaway greenhouse where lead melts on the surface.
Yeah.
You need a way to take carbon out of the atmosphere too.
And that's what the subduction does.
Indirectly, yes. It starts with weathering. Rain falls on fresh rock often pushed up by tectonics. The chemical reaction pulls carbon out of the air and locks it into minerals. Those minerals wash into the ocean, settle on the seafloor, and eventually
that seafloor gets subducted.
Bingo. It gets dragged down into the mantle. So the Earth burps out carbon through volcanoes and then eats it back up through subduction. It's a planetary thermostat. It keeps the climate stable within a habitable range over millions of years.
So it prevents us from becoming an ice ball or a furnace. It's a self-correcting system.
Correct. Without plate tectonics, that cycle breaks. The thermostat breaks. Life as we know it needs that stability.
That's the part that gets me. We think of the climate as the air, but the climate is actually controlled by the rocks. And the source also mentions habitat creation.
Sure. I mean, by constantly changing the surface, moving continents, creating new oceans, lifting up mountain ranges, plate tectonics creates diversity. It isolates populations, forcing them to evolve. It creates shallow seas and deep trenches. That complexity drives evolution.
A stagnant planet would be a boring planet.
It might have life, but it probably wouldn't have the incredible diversity Earth has. Plus, there is that nugget about the very origins of life.
Oh, right, the hydrothermal vents.
Yes. Many scientists believe life may have started in those deep-sea hot springs, like the ones near Iceland and the mid-ocean ridges. Those chemical-rich, hot environments are powered entirely by this internal heat engine. So the engine might not just sustain life, it might have sparked it in the first place.
That is incredible. We owe our existence to the slow-motion churning of the mantle. But, and here's where the story takes a bit of a turn.
Yeah.
Nothing lasts forever.
No. Even geological processes have a lifespan. This brings us to the future.
The dying engine. We established that this is a heat engine, and like any engine, it runs on fuel. And we said that fuel was primordial heat and radioactive decay.
And both of those are finite resources. We're using them up.
The primordial heat is just leaking out into space.
Yes, Earth is cooling down. It was much hotter when it was young. It is cooler now than it was 2 billion years ago, and it will be cooler still in the future. We're radiating heat out into the vacuum faster than we are generating it.
And the radioactive fuel pellets.
They are decaying. Half-life by half-life, they're turning into stable elements that don't produce heat. We are slowly running out of nuclear fuel.
So the planet's thermostat is turning down. What happens when the engine gets too cold? Does the taffy stop flowing?
Eventually, yes. The mantle will become too stiff to convect efficiently. The friction needed to drive the plates will change. The engine will sputter.
So the conveyor belt stops.
It slows down, and eventually it halts. The source estimates that in roughly 1 billion years, the reduced heat flow might slow plate motions significantly.
And when the plates stop, the recycling stops.
The carbon cycle stops. Volcanoes wane and go extinct. The mechanism that pulls carbon out of the air stops. The mechanism that puts it back in stops.
So Earth loses its ability to regulate its own climate?
It does. It essentially becomes a dead planet geologically. It joins Mars in the retirement home of planets. The magnetic field might also fail because that is driven by the core's heat, too.
That is a very sobering thought. We are living in a temporary window.
We are. We are here during the active geology phase of Earth's life. And that phase coincides with the habitable period. The active geology is what allows the habitability. When the geology dies, the habitability likely dies with it.
It really makes you realize that a planet isn't a static thing. It's a life cycle. It has a birth, a vibrant middle age, where we are now, and an eventual decline.
It puts the extraordinary in extraordinary facts. It's not just that Earth has plate tectonics. It's that we are here at the right time to benefit from them. We are surfing the sweet spot of the planet's thermal history.
Just surfing on a slab of rock the size of India, hoping the soup doesn't get cold too fast.
That's one way to put it. But don't worry, we have about 1 billion years. The sun will probably become a problem for us long before the geology does.
Good to know, I guess. It's amazing to think that the very stability we rely on, the climate, the atmosphere, the oceans, is all maintained by this violent, crushing, grinding process happening right beneath us. We usually think of earthquakes as disasters, as interruptions to our peaceful lives. But in the big picture, the earthquake is the heartbeat of the planet.
Without that heartbeat, the planet dies. The grinding plates are the machinery of life.
So next time you feel a tremor or see a picture of a volcano or even just look at a mountain range, remember that you are looking at the engine at work. A 47 terawatt engine that has been running for 4.5 billion years to keep the lights on for us.
And it's a reminder to appreciate it while it lasts. Because 1 billion years from now, things might be very quiet around here.
A little too quiet. It's a lot to process. We were standing on a dying engine, but it's the best engine in the solar system.
Absolutely. It's the engine that makes Earth, Earth.
Well, I think that gives us plenty to think about regarding what's happening under the floorboards. It's not just rock, it's power. That covers 7. Ready for the next one? Let's head to fact 6. Welcome back. We are moving right along in our countdown. Let's dive into fact number 6.
Fact number 6. And this one. This is where we stop looking up at the stars for a moment and look down. Deep down.
Right, because usually when we talk about what makes Earth habitable, the whole blue marble thing.
We talk about oceans, oxygen.
Exactly. The perfect distance from the sun. But this fact argues that the real hero is something we will never see.
That's it. We're talking about a mechanism that's roughly the size of the planet Mars.
Buried thousands of kilometers under our feet.
And it generates a planetary scale force field.
It honestly sounds like something straight out of science fiction. A hidden generator creating a shield to deflect, death rays from space.
But it's not fiction at all. It's geophysics. We're talking about the liquid iron geodynamo.
The planetary magnetic shield.
It really is the unsung hero of all complex life. Without this shield, Earth would be a radiation-blasted wasteland.
Okay, so let's unpack this. Because it's one of those things where we can't just go visit the source, right? We can't drill down to the core.
Not even close.
But we can see the evidence of it. I was reading the notes about standing in the Norwegian Arctic, and it just paints such a vivid picture. You're there, it's pitch black, freezing cold, and the sky just catches fire.
The aurora borealis, yeah, it is spectacular.
Beautiful, for sure. These curtains of green and crimson light just rippling across the sky. But the thing that stuck with me is that we see it as art, but it's violence. It's a crash site.
That is a fantastic way to frame it. It is a cosmic battleground, really. The sun is constantly shooting these streams of high-energy charged particles at us.
The solar wind.
The solar wind. And the aurora is basically the shrapnel from those particles slamming into our atmosphere.
So it's like tracer fire hitting the shield.
In a way, yes. Those charged particles, electrons, protons, they're hurtling toward us.
Right.
But they don't just hit the surface. They get snagged by Earth's magnetic field lines.
And this is the key visualization, right?
It is. Those field lines, they act like a giant funnel. They guide those particles, spiraling them down toward the north and south poles.
The source used that image of water spiraling down a drain. So the solar wind is the water, the magnetic pole is the drain.
And the glowing light, the aurora, that's the splash when it finally hits the atmosphere.
So what's happening there, physically?
Well, when those particles spiral down and they smash into oxygen and nitrogen atoms way up in the atmosphere, they excite them. The atoms literally glow to release that extra energy.
And the color depends on the atom.
Exactly. Green for oxygen, sometimes red, blue or purple for nitrogen.
So every time we see that light show, we're basically watching our magnetic field do its job. It's diverting all that dangerous traffic.
It is. Now let's think about the structure of that diversion. You remember that old iron filings experiment from school?
Oh, definitely.
Yeah.
You scatter the filings over a bar magnet, you tap the paper, and boom, you see these invisible loops just appear.
Right. Now scale that up to the size of a planet. Earth's magnetic field lines, they arch out of the South Pole, curve thousands and thousands of kilometers into space, and then dive back into the North Pole.
Creating this massive bubble, the magnetosphere.
That's our shield.
But this is where the school science version kind of breaks down. Because in school, we use a permanent magnet, a solid bar of metal. Earth can't be that, right? I mean, the core is, what, 6,000 degrees Celsius?
You've hit on a crucial point. It's called the Curie temperature. If you heat a permanent magnet past a certain point, the thermal agitation just scrambles the atoms.
And it loses its magnetism.
Completely. And Earth's core is way, way past that point.
So it's physically impossible for it to be a giant fridge magnet.
Yeah.
It has to be something active. It has to be an electromagnet.
Exactly. It's a dynamo. And this is where that industrial engine comparison really holds up. We're not standing on a solid rock. We're standing on top of a churning liquid metal ocean.
That is the part that still freaks me out a little bit.
Yeah.
The outer core. Almost 3,000 kilometers down. It's not rock. It's liquid iron.
A vast ocean of liquid iron and nickel, darker than you can imagine, under pressures exceeding 1 million atmospheres, and it is moving violently.
Okay, so the source material called it an inverted bicycle dynamo. And I think I get how a normal bike dynamo works. You spin a magnet near a wire, and you get electricity for your light.
Motion creates electricity.
Right. But how does Earth invert that?
Okay, so think about the ingredients. In your bike dynamo, you move a solid magnet to create a current in a stationary wire. In the Earth, we have a conductor, that massive ocean of liquid iron that is moving through a magnetic field that already exists.
Ah, okay, so you have this moving liquid metal rushing through a magnetic field. That has to generate an electric current.
It generates massive electrical currents. I mean, we're talking billions of amps. And here is the magic trick of what we call a self-exciting dynamo.
Let me guess. Those new currents.
They generate new magnetic fields.
So it's a loop. The motion makes the current makes the field, and the new field interacts with the motion to make even more current.
It feeds itself. It's a self-sustaining feedback loop. As long as that iron keeps moving, and this is key moving in the right way, the generator stays on.
Let's talk about that movement, because it's not just sloshing around randomly like water in a bucket. The source used this really visceral description of the magnetic field lines being stretched and twisted like taffy.
Visualizing the field lines as physical things really helps here. Imagine them like, I don't know, elastic bands embedded in that liquid iron.
Okay.
As the iron flows and churns, it drags those elastic bands with it. It stretches them out, twists them, folds them back on themselves. And that stretching, that actually adds energy to the field. It intensifies it.
And the fact that the Earth is spinning must organize that chaos somehow.
The Coriolis force. It's the same force that makes hurricanes spin on the surface, but it's at work 3,000 kilometers down.
But instead of clouds, it's organizing molten iron.
It forces the upwelling hot iron into these massive spirals. The technical term is columnar vortices.
So you're saying to picture tornadoes of liquid iron, all aligned roughly with the north-south axis, just spinning wildly.
Dozens of them. And these organized spirals are what turn that chaotic energy into a structured, a dipolar magnetic field. It's like lining up Billions of tiny little batteries, so they all work together.
It really creates this image of the Earth as a machine, a heat engine. Because this can't all happen for free, right? There's no perpetual motion. It needs fuel.
No, thermodynamics always gets its say. The engine needs a source of energy, and the fuel is the Earth itself, just cooling down.
And this connects to the solid inner core. I don't think a lot of people realize the inner core is actually getting bigger.
It is very slowly. As the Earth radiates heat out into space, the very bottom of the liquid outer core cools down, and the iron freezes onto the solid inner core.
So our planet is freezing from the inside out.
That's a good way to put it. And when things freeze, they release heat. It's called latent heat. Plus, the solid inner core is mostly pure iron, so when the liquid freezes onto it, it leaves behind lighter elements.
Like what?
Oxygen, sulfur, silicon. Those lighter elements are now buoyant. They're like bubbles. They start to float upward through the heavy liquid iron.
So you got heat rising, and you've got these chemical bubbles rising. That's what's stirring the pot. That is the convection.
That is the driver.
Yeah.
That powerful vertical motion, twisted sideways by the planet's spin, is what powers the whole dynamo. We are, in a very real sense, converting the thermal energy of a slowly dying planet into magnetic energy.
The thermal energy of a dying planet.
Yeah.
That is both poetic and a little bit ominous.
What's a long, slow death?
Which brings us to stability. Because if it's a fluid system, if it's based on these swirling tornadoes of metal, it can't be perfectly stable.
Oh, it's definitely not. It wanders. The magnetic North Pole is currently racing from Canada towards Siberia.
How fast?
About 50 kilometers a year right now. It's speeding up.
Okay, but wandering is one thing, flipping is another. This is the part of the source material that always grabs the headlines. Magnetic reversals.
The flip. Yes, it sounds very catastrophic.
It sounds like the end of the world. The compass points south, the shield goes down, birds fall out of the sky. How much of that is just Hollywood versus reality?
Well, let's look at the data. We know for a fact these reversals happen. We see it frozen in the geological record.
The magnetic striping on the ocean floor.
Exactly. It's like a barcode recording the field's direction over millions of years, and it has flipped hundreds of times.
And the process, it's not instant, right? It's not like flipping a light switch.
No, not at all. And that's the messy part. A full reversal can take anywhere from 1,000 to maybe 10,000 years to complete. And during that transition, the main dipolar field, that nice, neat north-south structure, it breaks down.
So we wouldn't just have a north and a south pole. We might have 4 poles. Or 8.
You got it. You might have a North Pole sitting over the Sahara, another one over the Pacific. The field becomes complex, multipolar, and crucially, the overall strength of the shield drops.
That's the real worry, isn't it? If the shield drops to, say, 10% of its normal strength, what happens to us on the surface?
Biologically, we'd probably be okay. Life has survived hundreds of these reversals. There is no major mass extinction event that lines up with a magnetic flip.
So we don't get fried by cosmic rays.
The atmosphere itself is still a pretty good shield, but our technology, that is a very different story.
Right. The dinosaurs didn't have GPS satellites or continent-spanning power grids.
Exactly. If we went through a reversal today with a severely weakened shield, we would be much more vulnerable to solar storms. Satellites could be fried in orbit. The entire GPS network could degrade or fail. Power grids on the ground could suffer massive surges and blackouts.
So it's not an extinction-level event, but it could be a civilization reset-level event if we're not prepared.
It would be an incredibly expensive and chaotic time. But again, it's a slow process. We would see it coming for centuries.
That's mildly comforting, I guess.
Yeah.
But there's a scenario worse than a flip. A flip is just the engine sputtering and changing gears. What happens when the engine finally runs out of gas?
That is the ultimate fate of every terrestrial planet. Eventually, the core cools down enough that the convection stops, the dynamo stalls, the engine dies.
And we have a neighbor who has already gone through this. The ghost of Christmas future.
Mars.
Mars.
Mars is the perfect cautionary tale. We look at it today. A cold, dry, rusty desert with a paper-thin atmosphere. But all the evidence suggests that 4 billion years ago, Mars was wet. It had rivers, maybe even oceans. It had a thick atmosphere.
And it had a dynamo.
It did. We see magnetized crustal rocks on Mars that prove it once had a global magnetic field. But Mars is much smaller than Earth. It has less mass to hold on to its primordial heat.
So it cooled down much faster.
Much, much faster. Sometime around 4 billion years ago, the Martian core cooled enough to stop convecting. The dynamo shut down, the force field vanished.
And that's when the solar wind started to do its real damage.
It was a slow, relentless execution. Without that magnetic bubble to deflect the solar wind, those high-energy particles started slamming directly into the upper atmosphere of Mars.
It's like atmospheric sandblasting, right?
Yeah, precisely. Solar wind erosion. It just stripped away the lighter atoms bit by bit. Water vapor was split apart, the hydrogen was lost to space, and over hundreds of millions of years, the atmosphere was thinned down to less than 1% of Earth's pressure.
And once the atmosphere goes, the water goes. It either freezes solid or boils away into space. The planet dies.
And the surface becomes sterilized by radiation. That is the fundamental difference between Earth and Mars. It's not just distance from the sun, it's the fact that our engine kept running.
And our engine has been running for at least 3.5 billion years.
That's what the paleomagnetic data from ancient rocks tells us. For 3.5 billion years, that churning ocean of iron has been standing guard. It allowed our atmosphere to stabilize, the ozone layer to form. It let complex life crawl out of the oceans without being irradiated to death.
It's just wild to think that my ability to sit here and breathe this air is directly connected to a magnetic tug-of-war happening 3,000 kilometers straight down.
It completely reframes how you view a planet. We think of the environment as the trees and the air and the water. But the deep interior is the foundation of that environment. If the core dies, the surface dies.
So do we need to worry about our core dying? You said it's cooling. Is the tank running low?
The tank is slowly emptying, yes. But you have to remember, Earth is big. We have a lot of leftover heat from our formation and a lot of radioactive elements like uranium and thorium in the mantle that act like a slow-burning furnace.
So give me a timeline. When does the engine stop?
Billions of years from now, the sun will likely expand into a red giant and boil our oceans away long before the core completely freezes solid and the dynamo finally stops for good.
Okay, so we don't need to start hoarding magnets for good. But this knowledge, this understanding of how a dynamo works, isn't just about Earth's history anymore. It's actually becoming a tool for hunting for life elsewhere.
This is one of the most exciting new frontiers in astrophysics. We're finding thousands of exoplanets now, planets around other stars. And the first question is always, is it in the habitable zone? Could there be liquid water?
But now we have to ask a new question. Is the force field up?
Exactly. We're starting to realize that a magnetic field might be a primary requirement for long-term habitability. You can have a planet in the perfect temperature zone, the Goldilocks zone, but if it doesn't have a working dynamo, it might just be a stripped-down, barren rock like Mars.
So a magnetic field is almost a biosignature, or at least a habitability signature.
It's the roof on the house. You don't start checking for furniture if the house doesn't even have a roof. If we can detect the kind of radio emissions that suggest a strong magnetic field on an exoplanet, that planet immediately moves way up the list of interesting places to look for life.
It's just amazing how this one mechanism connects everything. For the tiny atomic collisions that create the aurora, to the giant churning of the core, to the death of Mars, and now the search for life across the galaxy.
It really is a universal principle. If you want a living planet, you probably need a living core. You need that heat engine.
I think that's what I'm going to take away from this. I usually think of the ground beneath my feet as, well, solid ground, static, unchanging, but it's not.
Not at all.
It's active.
Yeah.
It's churning. It's a machine. And that machine is maybe the only reason we're here.
It's a violent, dynamic process that paradoxically creates a safe harbor for us on the surface.
And the aurora.
The aurora is the dashboard light. As long as you can see that light is on, you know the engine is running and the shields are holding.
The shields are holding.
Oh.
I love that. It makes me feel a little less fragile in this big, scary universe. We've got a bodyguard.
A big, molten iron bodyguard.
That covers 6. Ready for the next one? Let's head to fact 5.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 5.
Number 5. And this is the one where we finally stop looking down at the planet and start looking up.
We are talking about the sky, the atmosphere. And going through the research, I had this realization about how I see it. I think most of us, our default setting is just the sky is infinite. You walk outside, you look up, and it goes on forever.
It's the ultimate optical illusion.
Yeah.
It really is. It's a trick of perspective because, we're tiny creatures on a huge sphere. So, of course, it feels limitless. It feels, robust.
Right.
But the whole mission of this deep dive, or fact number 5, is to just completely shatter that illusion. We have to recalibrate our sense of scale.
And the sources do that really well, I thought, right from the start. They change our vantage point. They put us on the International Space Station.
Yeah.
So let's just try to visualize that. You're floating 400 kilometers up, looking out the window at the horizon. You're not seeing an endless blue ocean of air.
No, not at all. And this is a view that, astronauts talk about all the time. They call it the overview effect. It's almost a spiritual thing for them. You see the curve of the Earth, and just hugging it is this impossibly thin, glowing blue line. From space, the atmosphere. It doesn't look like an ocean. It looks like a contact lens.
One of the articles used the term gossamer shell, and I really paused on that. Gossamer just sounds so fragile.
It's the perfect word for it. Because to really understand Earth's biology, its physics, you have to get your head around just how razor thin that shell is. And, for that, we need some good analogies.
Right, everyone's heard the apple skin one, right? That the atmosphere is like the skin on an apple.
Yeah, that's the classic.
But the basketball analogy in the source material felt, I don't know, even more visceral to me.
It's a bit more precise, I think, especially for the breathable part of the atmosphere. So if you scale the Earth down to, say, the size of a standard basketball, the troposphere, so where all the weather is, the clouds, where we live, it isn't even the thickness of the leather.
No.
It's the thickness of a single sheet of printer paper wrapped around that ball.
That is a sobering image. You hold a basketball, you wrap one piece of paper around it, and you realize that's it. That's the only thing between us and the vacuum of space.
And we can make it even tighter. I like to call this the vertical drive visualization.
Ah, I liked this one. Okay, so I'm in my car,
Right.
but instead of a road, I'm on some magic highway that goes straight up. I'm doing what? Highway speeds? 100 kilometers an hour, maybe 60 miles per hour?
Yeah, just cruising. Straight up. How long do you think it would take until you're in a zone where you literally can't survive without a pressure suit?
I don't know, an hour maybe? A couple of hours?
About 10 minutes?
10 minutes. I spend more time than that looking for parking at the grocery store.
Think about that. In the time it takes to listen to just the first few minutes of this conversation, you would have driven past all the breathable air, past the clouds. You'd be entering the lethal freeze of the upper layers.
So everything that's ever happened, every person who's ever lived, every war, every invention, all happened in a vertical space I could drive through on a quick coffee run.
Exactly.
It just reframes the whole planet. We're not living on a rock with some big comfy blanket of air. We're clinging to a rock wrapped in saran wrap.
And that saran wrap, it isn't just one thing. It's a complex machine. It's like a layer cake of physics and chemistry.
Okay, so let's cut into that cake. The sources break it down into these distinct zones. If we're coming down from space, driving that car back home, what do we hit first?
Well, coming down from the vacuum, you'd hit the mesosphere at about 100 kilometers up. That's the Kármán line, which is sort of the official edge of space.
The mesosphere, that's the shield, isn't it? That's where meteors burn up.
It's the incinerator, yeah. The air there is incredibly thin. It's almost a vacuum, but it's just dense enough to create friction.
Ah. Yeah.
So when a meteor slams into it at 30,000 miles per hour, the air molecules can't get out of the way. They compress.
And compressing a gas creates heat.
Intense heat. The rung just vaporizes. So when you're in your backyard and you see a shooting star, you're actually watching the mesosphere do its job.
Okay, so we make it through the incinerator. Now we're maybe 50 kilometers up. We're in the stratosphere.
Right, and this is where things get a bit counterintuitive. Down here, in the troposphere where we live, the higher you go, the colder it gets.
Right, like climbing a mountain.
But in the stratosphere, the higher you go, the warmer it gets.
Wait, really? It gets warmer as you go away from the Earth. How does that work?
It's the ozone layer. The stratosphere is home to the ozone layer, and ozone molecules are amazing at absorbing ultraviolet radiation from the sun. When they absorb that energy, they vibrate, they release heat. So you've got this layer that's being heated from above by the sun, not from below by the Earth.
And that's our planetary sunscreen.
It's more than sunscreen. I mean, without the ozone layer soaking up all that high-energy UV, the surface of the Earth would be sterilized. DNA literally breaks down under that kind of radiation. Life on land couldn't even exist until the ozone layer formed.
So we have the meteor shield, then the UV shield, and then the last leg of the journey, the troposphere.
The bottom 12 kilometers or so, this is the soup.
The soup.
It's dense, it's wet, it's turbulent. This little layer has 75% of the atmosphere's entire mass and basically all of its water vapor. This is where the weather is.
It's funny you mentioned turbulence because the source noted that cruising altitude for a jetliner is right at the boundary.
Yep, pilots call it the tropopause. It's basically the ceiling of the weather. when you're on a plane and you see that perfect flat deck of clouds below you.
You're looking at the top of the troposphere.
You're above the storm. The plane flies up there because the air is thinner, so there's less drag. And you're physically surfing on top of the weather layer.
But even inside that soup, the pressure changes are just drastic. Like with Mount Everest, it's still in the troposphere, but you can't breathe there.
Everest is the perfect example of how fast the gas runs out. The summit's at 8.8 kilometers. That's not even that high, remember our 10-minute drive.
You're barely 5 minutes into the drive at that point.
Right. But the air pressure there is only 1/3 of what it is at sea level.
So gravity pulls the air down so hard that just 5 miles up, 2/3 of the entire atmosphere is already below you.
Exactly. So every breath you take on Everest gives you only 33% of the oxygen you'd get at the beach.
It really hammers home that we're bottom dwellers. We're like deep sea creatures living at the bottom of this ocean of nitrogen and oxygen. We're built for high pressure.
It's a very fragile niche.
Yeah.
Now, moving on from the structure, I really want to get into the mechanics. The sources kept calling the atmosphere a machine. It's actively doing work.
Right, it's not just a passive blanket. It has 3 main jobs. It's a shield, which we talked about. It's a transport system. And this is the big one, it's a thermostat.
Let's talk about the thermostat, because this gets into the greenhouse effect, which is a term that gets thrown around a lot, usually in a negative way.
Yeah, in the context of climate change.
Right, but the baseline effect.
Yeah.
We would be dead without it.
Dead is an understatement. We'd be a snowball. The notes I have say that if you took away the atmosphere, specifically the greenhouse gases, Earth's average temperature would be minus 18 degrees Celsius.
Just think about that. Minus 18 Celsius. As a global average, the oceans would freeze solid.
Yeah.
Life as we know it would just stop.
But because the atmosphere traps some of that heat, our actual average is around plus 15 Celsius.
That's a 33-degree swing. 33 degrees. That's the entire margin that allows for liquid water and therefore for life. It's insulation.
But it doesn't just hold heat still, it moves it around. That was the transport system part.
Exactly. The equator gets way more direct sun than the poles. If that heat didn't move, the equator would be boiling and the poles would be, absolute zero. The jet streams, the hurricanes, they're just giant convection currents.
Moving heat from the middle to the ends.
Yeah, balancing the books. And it's moving water, too. That whole atmospheric river concept was just fascinating. A conveyor belt picking up water from the Pacific and dropping it as rain on Iowa.
Without that, the continents would just be deserts.
Totally. The land needs the ocean to water it, and the atmosphere is the bucket brigade.
There was one detail in the data, though, that I found almost poetic. The idea that the atmosphere actually breathes.
Ah, you're talking about the Keeling curve. It is one of the most beautiful data sets in all of science.
So if you plot global carbon dioxide over a year, it's not a flat line.
No, it's a jagged sawtooth wave. It goes up and down every single year.
And that's not just noise.
No, that's the biosphere. Look at a map. Most of the planet's landmass is in the northern hemisphere.
North America, Europe, Asia, right?
That's where the big forests are. So when it's summer in the north, you get this massive explosion of leaves, of photosynthesis. The forests of Siberia and Canada and the US, they all just inhale.
Yeah.
They suck gigatons of CO2 out of the sky.
So global CO2 levels actually drop every summer.
They do. And then in the northern winter, all those leaves fall, they decay, they release that carbon back. The planet exhales. You can literally see the lungs of the Earth working in the chemistry of the sky.
That brings us to the biggest twist in the source material, I think. We tend to assume, Earth had an atmosphere and so life could evolve.
But the sources argue it's the other way around.
Life evolved and so Earth has this atmosphere.
That's the critical insight. The atmospheres on Venus or Mars, they're just dead chemistry, mostly CO2. Earth's atmosphere is a biological construction. It was built by life, for life.
And this is the story of the Great Oxidation Event.
It's the greatest drama in Earth's history, arguably. For the first 2 billion years, there was no free oxygen in the air. If you took a time machine back then, you'd suffocate instantly.
So where did the 21% oxygen we breathe come from?
Tiny little organisms in the ocean. Cyanobacteria. About 2.4 billion years ago, they basically hacked photosynthesis. They figured out how to split water molecules using sunlight.
And oxygen was just the waste product.
It was their exhaust fume. And here's the kicker. For all the other life on Earth at the time, which was anaerobic, oxygen was a deadly poison.
So the first time life really changed the atmosphere on a global scale, it caused a mass extinction.
The worst one in history. They polluted the entire planet with oxygen and wiped almost everything else out.
Yeah.
But that pollution created the ozone layer, and it allowed for high-energy aerobic metabolism. You can't have a big brain or a fast predator without oxygen as a fuel.
So every breath I take is technically the waste product from a bacteria that almost killed the planet 2 billion years ago.
We are living in their terraformed world. We are the beneficiaries of ancient pollution.
But that leads to the elephant in the room. If the atmosphere is a biological construction and it's this thin, that must make it vulnerable.
It does. We are basically watching the sequel to the Great Oxidation Event right now. Only this time, we're the cyanobacteria.
We're talking about the changes to CO2.
Yes. And I want to be specific with the numbers here because people hear 0.04% and they think, well, that's tiny. How can such a tiny amount matter?
Right. Pre-industrial levels were about 0.028%. Now we're over 0.042%. It sounds like a rounding error.
But think about it like alcohol in your blood. At 0.04%, you're fine. At 0.08%, you're legally impaired. You can't drive. Tiny percentage changes in complex chemical systems can have massive functional outcomes.
That's a really good way to frame it. It's not the volume, it's the potency.
And it's the rate of change. Nature adjusts the thermostat over tens of thousands of years. We've just cranked it up by 50% in about a century. We are hitting the fast-forward button on a geological process.
And because we know how thin that shell is, that sheet of paper on the basketball, we know there isn't some infinite buffer to absorb the shock.
That's the fragility versus robustness paradox.
Yeah.
The atmosphere is robust enough to power a hurricane, but it's chemically fragile. It's a very specific formula, and we're rewriting the recipe while we're still living inside the test tube.
There was another angle to this thinness that I hadn't really thought about before. The gravity well, the fact that this layer is both our life support and our prison.
It's the great irony, isn't it? We live at the bottom of a deep gravity well. To leave, you have to fight your way up through the thickest part of the atmosphere and hit an insane speed like 40,000 kilometers an hour. It is incredibly hard to get out.
So realistically, we're stuck here.
For the foreseeable future, yeah. This 10-minute drive of air is the only habitat we have. It makes you realize how precious this spot is. We are effectively trapped in a paradise that we were actively redecorating.
And connecting this to the bigger picture, you said Earth's atmosphere is a biological creation. Does that mean if we're looking for life on other planets, their atmosphere is the clue?
That is exactly where astrobiology is now. We're looking for biosignatures.
So if we point the James Webb Telescope at a planet 50 light years away,
we analyze the light that passes through its air. And if we see an atmosphere that's in chemical equilibrium, say it's all CO2, it's probably dead. But if we see oxygen and methane together,
that's a smoking gun.
It is. Because oxygen is super reactive. It wants to bind with rocks, with other elements. It shouldn't be there unless something is constantly pumping it out.
A biosphere.
Exactly.
Yeah.
An oxygen-rich atmosphere isn't just a gas. It's a signal. It's a planetary scale engineering project. You're seeing life.
That completely changes how you look at the sky. It's not just blue space. It's a beacon broadcasting life is here to the rest of the cosmos.
And it's the only roof we've got.
So to bring this all back, we started with this illusion of infinity.
And we found a gossamer shell, a single sheet of paper wrapped around a basketball.
We found a machine that shields us, warms us by 33 degrees, and moves water and heat around the globe.
A machine built by ancient bacteria and maintained by the seasonal breath of the forests.
And a machine that we are now tinkering with at an unprecedented speed. It makes you want to just take a deeper breath while you can.
And appreciate just how much work went into making that single breath possible.
It's not empty space. It's the most important structure in the universe, at least for us.
A very thin, very vital blue line.
That covers 5. Ready for the next one? Let's head to fact 4.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 4.
You know, when we talk about water, we usually think of it as a resource, something to drink, something that falls from the sky.
Right.
But today, we are going to completely reframe how you look at the most defining feature of our planet. When you visualize Earth, you see the blue marble, right?
Oh, absolutely. I see the Pacific, the Atlantic, swirling clouds, and it immediately makes me think of, that diagram from 4th grade science class.
The water cycle, yeah.
The sun heats the ocean, water evaporates, forms clouds, rains down on the mountains, and then it flows back to the sea. Rinse and repeat.
And that cycle is real. I mean, it's absolutely crucial for weather, for agriculture, for, filling our reservoirs. But the research we're looking at today argues that the surface cycle, that one is just the skin of the beast.
Just the cosmetic layer.
Exactly. We're talking about a hidden mechanism that defines the planet on a much, much grander scale. They call it the deep time global water cycle.
Deep time. That phrase. It always gives me goosebumps.
Yeah.
It sort of implies we're leaving human history behind and entering geology.
That's it, exactly. This isn't about rain falling today and evaporating tomorrow. This is a cycle that links the oceans to the deep interior of the Earth, the mantle, and it operates over hundreds of millions of years.
So the mission for this deep dive is to understand how the Earth essentially swallows its own oceans and then spits them back out.
That is the core of it. We're going to get into the mechanics, but more importantly, why this process is likely the only reason we have dry land to stand on at all.
That is a massive claim. You're saying without this deep cycle, no continents.
Potentially, yeah. We might just be a sphere of water.
Okay, let's unpack this. Because if the Earth is drinking the ocean, I need to know where the straw is. How does water physically get inside the solid Earth?
To find that straw, we have to go to the edge. I want you to visualize standing at the very bottom of the ocean, right at the edge of the Mariana Trench.
Deepest place on Earth. Crushing pressure. Total darkness.
Yeah. Right. And geologically, you're standing on the Pacific Plate. It's this massive, cold slab of the Earth's crust. And right there at the trench, it's bending. It's beginning this slow, grinding dive under the Philippine Sea Plate, into the mantle.
This is Subduction 101. One tectonic plate diving under another.
Correct. But here's the nuance that usually gets skipped. Imagine that ocean floor. It's been sitting under the Pacific for, maybe 100 million years. It's not just some smooth, waterproof tile. It's fractured. It's porous.
So it's waterlogged, like a plate that's been soaking in the sink.
It's actually much more intimate than that. It's not just that the cracks are filled with water. The chemistry of the rock itself has changed. When seawater interacts with rocks like basalt, especially hot water near hydrothermal vents, it gets chemically locked into the mineral structure.
So we aren't talking about little pockets of liquid water trapped in a hole.
No. We're talking about hydration at the molecular level. Think of rust. Rust is just oxidized iron, right? The oxygen is bound to the iron. Well, these rocks are hydrated. They turn into minerals like clays or a green rock called serpentinite. The water becomes part of the crystal.
Okay, that distinction matters. So when this plate dives into the trench, it's not pouring water down
a drain, exactly. It's carrying these hydrated minerals down with it.
It's a conveyor belt.
A conveyor belt of wet rock. And this conveyor belt is moving at a blistering speed of a few centimeters per year.
Wow. Glacial doesn't even begin to describe that.
But it's relentless. Now follow that rock down. As it descends, the conditions just get insane. We are talking pressures exceeding 100,000 atmospheres, temperatures climbing past 1,000 degrees Celsius.
I can't even wrap my head around 100,000 atmospheres. That's just, what does it even mean?
It means it's enough to distort the atomic structure of matter. And this brings us to a critical fork in the road for our water. As the rock gets squeezed and roasted, those hydrated minerals become unstable. They start to break down. The rock literally can't hold on to the water anymore.
It gets wrung out, like twisting a wet towel.
In a sense, yeah. This dehydration happens at different depths. Some of that water is squeezed out relatively early, maybe 100 kilometers down. This water then rises up through the mantle above it. And because water lowers the melting point of rock, it creates magma, and then boom.
Volcanoes.
Arc volcanoes, the ring of fire. When you see steam venting from Mount Fuji in Japan, you're actually seeing some of that subducted ocean water returning to the surface. It took the shortcut.
Okay, so that's the short cycle. Water goes down, gets squeezed out, melts rock, pops back up as steam. But you said this was a deep dive. What happens to the water that doesn't escape?
This is where the science has really evolved. A huge portion of that water stays locked in the colder parts of the slab and rides it down past the point of no return. It bypasses that volcanic exit ramp and just keeps going into the deep upper mantle.
And how deep are we talking now?
We are heading down to a layer called the transition zone. This is roughly 400 to 600 kilometers beneath our feet.
600 kilometers down.
Yeah.
For context, the International Space Station is only 400 kilometers up, so we're going deeper into the Earth than astronauts are high in the sky.
That's a great way to think about it. And this zone is where we hit the big aha moment of this fact. For a long time, geologists thought this layer was just more of the same dry, hot rock. But experiments and seismic data have shown something else. The minerals at this depth, specifically high-pressure versions of olivine called wadsleyite and ringwoodite, have a unique superpower.
They can hold water.
They have a storage capacity that is frankly mind-boggling. Because of the insane pressure, the crystal structure of these minerals opens up in a way that allows them to trap water components, hydrogen and hydroxide ions, within the rock itself.
How much water are we talking about here? A lake? An ocean?
Well, the estimates vary. Obviously, we can't go there and measure it, but the consensus in the sources is startling. The transition zone has the potential to hold several times more water than all of Earth's surface oceans combined.
Wait, pause there. You're saying there could be more water inside the rock of the mantle than there is in the Atlantic, Pacific, Indian, and Arctic oceans put together.
That is the implication, yeah. Beneath our feet right now is a reservoir that dwarfs all the surface water we can see.
My brain is immediately picturing Journey to the Center of the Earth.
Yeah.
You know, a giant underground ocean with dinosaurs swimming around.
I hate to be the one to do this, but we have to scrub that image. It's a common misconception. It is not a subterranean sea. You couldn't swim in it. There are no waves.
So if I drilled a hole 600 kilometers down, I wouldn't get a splash.
You would hit solid, incredibly hot rock. But if you analyzed that rock, you'd find it saturated with water on an atomic level. The source uses a cake analogy, which I think is really helpful here.
I'm always up for a cake analogy.
Think about a cake mix. You pour a cup of water into the batter, but after you bake it, you don't see pools of water inside the cake, right?
No, it's just cake.
The water has been incorporated into the structure. It's still there. It's what makes the cake moist, but it's not liquid water anymore.
That helps. So the mantle is the cake. The water is chemically bound inside the rock.
Exactly. It's solid water. But here is the key. Even though it's solid, it flows. Over geological time, the mantle churns. It convects. So this water is moving. And that brings us to the cycle part of the deep time water cycle.
Right, because if the trenches are constantly swallowing water and the mantle is storing it, eventually the oceans would just drain away, wouldn't they, if it was a one-way trip?
Precisely. For the oceans to remain stable, which they have for billions of years, there has to be a return leg. We have to look at the opposite of a trench. We have to look at the mid-ocean ridges.
The underwater mountain ranges where plates pull apart, the mid-Atlantic ridge.
Yes. Here, the mantle is upwelling. Hot rock is rising from those deep reservoirs to fill the gap. As that rock rises, the pressure drops. And just like opening a soda bottle, that drop in pressure allows the water to escape the minerals.
It outgasses.
It outgasses, it releases that trapped water back into the ocean. So you have this giant loop. Water goes down at the trenches, travels through the deep mantle for eons, and gets burked back up at the ridges.
The time scale on this must be unimaginable.
It is. The water molecules in your glass right now might have gone down a trench when the first dinosaurs were appearing, spent the entire Mesozoic era traversing the mantle, and only just came back up.
That is a staggering thought. It just blurs the line between geology and oceanography. They're the same system.
The source material uses a fantastic analogy for this. It compares Earth's water cycles to our own body, to our two circulatory systems.
Oh, I like this part. It really made it click.
So you have your systemic circulation blood pumping to your muscles, your brain. It's fast.
And that's like the surface water cycle. Rain, rivers, evaporation. Fast, dynamic.
Exactly. But you also have the pulmonary circuit, the loop to your lungs. It's vital, but it's for gas exchange, chemistry regulation. In this analogy, the deep time tectonic cycle is the pulmonary circuit.
And they go even further, calling the oceanic crust Earth's lung.
It fits perfectly. The oceanic crust is born at ridges. It absorbs water, that's the inhale. It transports it across the ocean floor, then dives into a subduction zone. There, heat and pressure squeeze the water out. That's the exhale.
And the water that stays deep is like nutrients being stored in the body's tissue.
Yes, exactly. It's a planetary metabolism. And just like your body has to regulate its fluids, the Earth uses this deep cycle to regulate the volume of the oceans. It acts as a planetary thermostat.
A thermostat for water volume. That implies sea level isn't just about melting ice caps. It's determined by the balance of this deep machinery.
Correct. And this balance is absolutely critical. Imagine if it broke. The source outlines two catastrophic scenarios.
Let's do it. Scenario A. What if subduction became too efficient? What if the Earth swallowed more than it burped out?
If we stopped returning water to the surface but kept swallowing it, the oceans would gradually drain into the mantle.
So eventually a reverse water world. The surface becomes a desert.
It would take about 1 billion years, but yeah, the oceans would disappear into the rocks.
And scenario B is if the outgassing wins.
Right. If the mantle released more water than subduction took in, the oceans would expand. They'd rise and rise, potentially drowning all the continents.
A true water world, no land at all.
And the amazing thing is, Earth's ocean volume has remained roughly stable for billions of years. That means these two processes, the swallowing and the releasing, have balanced each other almost perfectly for eons.
Is that just luck? Or is there a feedback mechanism?
It's likely physics finding an equilibrium. But this brings up a massive, kind of controversial idea from the notes called the water world hypothesis.
I flagged this. This is the idea that early Earth didn't always look like it does now.
Right. The theory suggests that early Earth, after it cooled, might have been completely covered in water. No continents, just a global ocean.
Because all the water was on the surface to start with.
Exactly. The idea is that the mantle hadn't started drinking yet. Plate tectonics, as we know it, hadn't fully kicked into gear.
So how do we get dry land? I always assumed the land just floated up because it's lighter.
It is lighter, yes. But this theory suggests the emergence of continents wasn't just about rock rising, it was about the ocean receding. Once plate tectonics started, the mantle began sequestering water. It essentially pumped the water level down.
Wait, so you're saying the only reason we have dry land today is because the mantle drank the excess water?
It's a very real possibility. Plate tectonics acted as a giant pump, lowering the sea level by locking water away deep in the mantle, allowing the continents to poke through.
That completely changes how I look at the ground. We're standing on the dry bits only because the Earth has this massive internal storage tank.
It connects everything, the geology, the oceanography, our very habitability. And when we look out at exoplanets, this becomes a crucial piece of the puzzle.
Because we're looking for other Earths. Right, we look for planets in the Goldilocks zone where water can be liquid.
We do. But this deep cycle suggests that just being the right distance from a star isn't enough. You need the internal machinery, too.
What happens if a planet doesn't have plate tectonics?
Well, look at Mars or Venus. They don't have this recycling system. But think about a stagnant lid planet, a super Earth, where the crust is too thick to subduct.
The lid is sealed tight.
Exactly. If the lid is sealed, you can't cycle water. Any water on the surface might eventually be lost to space, or if it's a water world, it stays a water world forever. You never get continents. You never get that mix of land and sea that seems so important for complex life.
So plate tectonics isn't just about earthquakes and volcanoes. It's the engine that keeps the water balance just right for life.
It keeps the water moving. That's the key. Habitability isn't a static state. It's a dynamic flow. It's all about the circulation. If the flow stops, the planet dies.
Let me get this straight then. The water down there allows the plates to move in the first place, right? It acts like a lubricant.
That's the paradox. It makes the mantle runnier, so convection is easier. Without that deep water, the mantle would be stiffer, and tectonics might just grind to a halt.
So the water allows the plates to move, and the moving plates are what cycle the water.
It's a self-sustaining loop. One requires the other. You don't get the deep water cycle without tectonics, and you might not get sustained tectonics without the water lubricating the engine.
That is the definition of a complex system. If you pull one thread, remove the water, stop the plates, the whole thing collapses.
And that is why Earth is so extraordinary. It's not one thing going right. It's a cascade of systems, heat, water, rock, all dancing together.
And we're just the beneficiaries on the surface, totally unaware of the massive industrial machinery grinding away beneath us to keep the oceans where they are.
I think it makes you appreciate the glass of water on your desk differently.
Right. It connects back to that idea in the source about where the water came from.
Yes, that the water you're drinking connects meteorites from billions of years ago to minerals 400 kilometers down. Every sip is a sample from a system that spans Earth's entire history. Some of those molecules arrived on a comet 4 billion years ago, then spent time in a cloud, then the ocean, then they got dragged into the underworld for 200 million years, then blasted out of a volcano, and eventually ended up in your tap.
It blurs the line between the surface world and the deep Earth. We think of them as separate. We live up here, the rocks are down there. But they're intimately connected. The surface is just the skin, and the water circulates through the whole organism.
It creates a sense of deep time. We live our lives in days and years, but the machinery keeping us alive operates on timescales that are almost impossible to grasp.
And it highlights how special Earth is.
Yeah.
We assume water is normal, but keeping liquid water on the surface for 4 billion years requires this complex hidden machinery.
Exactly. It's reassuring, in a way. The planet is holding on to its most precious resource tighter than we ever thought.
That covers 4. Ready for the next one? Let's hit a fact 3.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 3.
And this one is a big one. It's one of those ideas that really, it can fundamentally change how you see our planet.
We're talking about Earth's biosphere.
Exactly. But I need to be really clear. We're not talking about the biosphere you see out your window right now. This isn't really about the rainforests or, recycling. This is deeper. It's about the the raw nature of life itself.
Right. So the big idea here is that life on Earth isn't just old. It got started shockingly early, and once it started, it never let go.
You never let go. I mean, think about what Earth looks like in your head. It's probably a postcard, right?
Sure. Blue skies, green trees, oceans.
That is comforting. It's home. Well, for this, I need you to just, completely abandon that image.
Okay.
Because we're going to visit an Earth that is, for all intents and purposes, a completely alien world. A hostile one.
Alien feels right. We're talking about the Archean Eon. And to really get a feel for this, I think we have to do a little bit of a mental time travel.
Yes. We have to visualize it. So let's go back. 3.7 billion years.
Okay, I'm stepping out of the time machine. First thing, I probably need a spacesuit, right?
No, you absolutely do, 100%. Take a deep breath of that air and you'd suffocate.
What's in it?
Methane, ammonia. There's basically no free oxygen.
No.
It's a toxic soup. But even before you notice the air, you'd notice the light.
The light.
Yeah, the sun itself is different. Astronomers call it the faint young sun. It was maybe, 25% dimmer than it is today?
Which should mean the planet is frozen solid.
It should. But it wasn't. And that's because that toxic atmosphere we just mentioned was also a super effective greenhouse blanket. It was trapping every bit of warmth.
Yeah.
So it's dim, but it's also probably sweltering.
Dim but hot. Okay, what about the day?
Much shorter. The Earth was spinning way faster back then, so you're looking at a day that's only about 18 hours long.
18 hours. That's gonna make the weather just wild.
Wild and violent. And to make it worse, look up. The moon is in the sky, but it's huge. It looked way too big.
Because it was much closer to Earth.
So much closer. Which means the tides. I mean, forget gentle waves on a beach. We're talking about colossal tidal waves ripping across the planet every few hours.
So this is a chaotic place. Dim sun, giant moon, crazy tides, short days. What about the land itself? Am I standing on a continent?
Probably not. Not a big one anyway. The continents we know haven't really formed yet. You're most likely on a small volcanic island, just little bits of land sticking out of a global ocean.
And I'm guessing that ocean isn't the nice blue color I'm used to.
Not even close. Would have had a distinct greenish hue.
Green. From what? Algae?
No, from iron. Dissolved iron. With no oxygen in the atmosphere to make it rust, the oceans were just saturated with it. A global green, metallic-tasting ocean.
Okay, so let's just pause and paint this picture. I'm on a steaming volcanic rock looking out at a green iron ocean. There's a giant moon in the sky, a dim sun, and I'm suffocating on methane.
And there are lightning storms everywhere. It's a hellscape. By our standards, it truly is.
And yet, this is where we find it. This is where life is.
This is it. So if you walk down to the shore of that green ocean, there are no plants, no animals, nothing like that. You have to look closer. In the shallow water, you'd see these lumpy, dome-shaped rocks.
Stromatolites.
Stromatolites. They look a bit like, I don't know, stony cabbage heads. And they are just carpeting the seafloor.
And these aren't just rocks. They are alive.
They are cities. A stromatolite is a layered community of microbes. It's a mat.
How does that work? Like a vertical ecosystem?
That's a perfect way to put it. The top layer, it's all slimy and it's full of bacteria doing photosynthesis, soaking up that faint sunlight.
Okay.
But the layers beneath, in the dark, they're living off the waste from the top layer. They're processing things like sulfur and all that iron from the water.
So the penthouse gets the sun and the basement handles the heavy industry.
Exactly. And as they grow, they trap sediment layer by layer and turn into stone. And the most amazing part is, we have the receipts. We found their fossils.
Right, in Greenland and Australia.
Yeah, these fossilized structures, 3.7 billion years old. And we know they're from life because they have these chemical signatures, a specific ratio of carbon isotopes that, as far as we know, only biology can create.
Which brings us to the timing. Because 3.7 billion years is just, it's a number our brains can't really process.
That's just too big. It's abstract.
So let's use that 24-hour clock analogy to really unpack this.
I love this analogy. It's the only way to really feel the scale. So, okay.
Yeah.
Let's compress Earth's entire 4.5 billion year history into one day.
Midnight is the very beginning. Earth forms.
Right.
A molten ball of rock. For the first few hours, it's just chaos, asteroids, magma, oceans. But then, by around 4 a.m., things have cooled down enough for water to condense. The oceans form.
So the planet is wet. The stage is set. And this is the mind-blowing part. By 5 a.m., life is already there.
Just 1 hour later.
1 hour later on our clock. Life didn't wait. And to put that into perspective, you have to fast forward. When do complex animals show up? The things with legs and eyes and shells.
Much, much later, I'm guessing. 9 at night. So from 5 in the morning until 9 at night.
It was just microbes. For 16, 17 hours of Earth's day, single-celled organisms had the entire planet to themselves. No plants, no fish, no insects, just slime.
They didn't just live here. They owned the place.
We terraformed it. And just to really hammer the point home, what about us, humans?
Oh, boy. Late to the party.
We show up at 11:59 p.m. and 58 seconds.
2 seconds to midnight.
2 seconds. All of human history, we just walked in the door as the credits were rolling. That is humbling. But let's go back to that window. Between 4 a.m. and 5 a.m. That seems impossibly fast.
It is. That's the shockingly early part. Because before 4 a.m., the Earth was uninhabitable. It was being slammed by sterilizing, ocean-boiling asteroids. That period, the late heavy bombardment, only ended around 4 billion years ago.
And by 3.7 billion, we have life.
That's a window of only a few 100 million years. In geological time, that's nothing. It's a blink of an eye.
It's like the moment the coast was clear, life just burst into existence. It was impatient. It suggests that maybe the jump from chemistry to biology isn't that hard, that it's something chemistry wants to do. Okay, so life gets started fast, but then it has to survive. And that's the other half of this, the persistence.
Right.
It's one thing to be born, it's another thing to survive what early Earth threw at you.
And it threw a lot. You mentioned the asteroids.
Yeah, and not just the small ones. We're talking about impacts so big they would have literally boiled the oceans away.
Boiled them? How does anything survive that?
By hiding. Deep in the rock, miles down.
Right.
Or clustered around hydrothermal vents at the bottom of the sea. They'd wait for the planet to cool and for the oceans to rain back down, and then they'd come out and recolonize.
That's incredible tenacity. And it wasn't just heat, right? The planet also froze over.
Completely. The snowball Earth events. The whole world encased in ice.
And then life almost poisoned itself.
Yeah, ironically. When photosynthesis really got going, it pumped out oxygen. And for the anaerobic life that dominated the planet, oxygen was a deadly poison.
The Great Oxidation Event. It was a mass extinction event caused by life itself. Exactly. But the key is life didn't die out. It adapted, it retreated, it evolved. The main point is that once life got its foothold at 5 a.m., it never, ever let go. It's almost impossible to get rid of. Once a planet has life, it seems like it has it for good.
That seems to be the lesson, yes. It's not fragile, it's a wildfire.
So what does all of this mean for the big picture, for, the rest of the universe?
That is the billion-dollar question in astrobiology. It really points to two very different possibilities.
Okay, what's option one?
Life is common. If it happened here so quickly, so eagerly, maybe that means it's an easy, inevitable step. You get liquid water and some carbon chemistry, and boom, you get life.
Which would mean places like Mars or Europa could be teeming with it.
It would give us a lot of hope, yeah.
But then there's the other side of the coin.
Option two.
We are an unbelievable fluke. Maybe we just got incredibly, ridiculously lucky.
A 1 in a trillion shot, and we're just biased because we're here to see it. Exactly. We look back and say, wow, that was fast. But maybe we're the only place it happened at all.
It really makes you think about how we separate things. We talk about geology and biology as two different subjects.
Right. Rocks and life.
But what you're describing is a world where there's no clear line.
There isn't one.
Yeah.
Those stromatolites, they are living things that became rock. The oxygen we breathe was made by biology. The iron falling out of the oceans was because of biology. The biosphere isn't just something sitting on the planet. For most of history, it has been a fundamental geologic layer of the planet.
We're living on a world where the boundary between life and rock is blurry.
It's completely blurry. And now, here we are, this little 2-second blip at the end of the day, using our consciousness to study those very same rocks to figure out where we came from.
59 p.m. arrivals trying to understand the 5:00 a.m. pioneers.
And we are directly related to them. Every single person listening is a descendant of that microbial slime. That chain of life has remained unbroken through every catastrophe for 3.7 billion years.
That's a pretty powerful thought. We come from some very, very sturdy stock.
It gives you a new respect for pond scum, doesn't it?
It really does. That pond scum built our world.
It did. It's the foundation of absolutely everything that came after.
That covers 3. Ready for the next one? Let's head to fact 2. Welcome back. We are moving right along in our countdown. Let's dive into fact number 2.
It is good to be back. And honestly, this specific fact is one of those that makes you look at the night sky a little differently. It sort of changes the texture of the silence up there.
I like that, the texture of the silence, because fact 2, it really sits on the edge of what we know for sure and what we desperately, hope is true.
Right.
But before we get to the existential dread, which I know is your favorite flavor, we need to set the scene. The source material for this one centers so heavily on the Kepler Space Telescope.
Right. The Planet Hunter.
But the way it hunted was, well, it was odd. I think most people imagine a telescope swinging around, scanning the whole galaxy like a lighthouse beam. But that's not what happened, is it?
No, and that's the critical piece of context here. To find what it found, Kepler had to be incredibly boring. I mean, truly obsessive.
Okay.
I want you to try this visualization and really, stick with it. Imagine you're standing in a pitch black field, total darkness, and you hold your arm out straight in front of you.
Okay, arm is out.
Now, pinch your fingers together, like you're holding a single grain of sand.
Got it.
Hold that grain of sand up against the dark sky. The patch of stars that Kepler monitored for years was about the size of that grain of sand.
That's it. A grain of sand against the entire universe.
That's it. But within that tiny, tiny footprint, Kepler monitored about 150,000 stars simultaneously. And it didn't scan them, it didn't blink, it stared at those points of light, unmoving, for 4 solid years.
That is a level of patience I just do not have, and all it was doing was watching for a flicker.
It was watching for shadows. That's the transit method. The idea is, it's pretty simple. If a planet orbits a star and the geometry is just right from our point of view, it'll cross in front of the star's face.
Right.
When it does, the brightness drops.
Right.
But we aren't talking about an eclipse here. We're talking about a dip in brightness of maybe, 1%? Or even hundredths of a percent.
Like a mosquito flying in front of a searchlight 2 miles away.
That's a perfect analogy.
Exactly.
Kepler was measuring the brightness of 150,000 searchlights, just waiting for a mosquito to fly in front of one of them. And the assumption going in was, well, we might find a few. Maybe planetary systems are rare.
But that is not what happened. The data came back, and it was loud.
It was deafening. I mean, that tiny patch of sky revealed thousands of planets. The extrapolation was immediate and, frankly, shocking. Planets are everywhere. There are likely more planets in our galaxy than there are stars.
Which is a heavy concept on its own. But here's where the story shifts. We didn't just find more planets. We found weird planets. And this is the part I really want to dig into, because the sources suggest that the discovery actually broke our understanding of how solar systems even work.
Oh, it absolutely shattered our models. Before Kepler, we had a very neat, very polite theory of formation. Small rocky stuff stays close to the star like Earth, Mars.
Sure.
Big gas giant, they form way out in the cold like Jupiter and Saturn. It makes perfect sense, physics-wise. Ice and gas survive better in the cold.
Elegant, it's orderly.
And it was wrong. Or at least it wasn't the whole picture. Kepler started finding these things called hot Jupiters.
Which sounds like a bad cocktail, but I assume it's a planet type.
It's a monster. Imagine a gas giant, even larger than our Jupiter. But it's orbiting its star closer than Mercury orbits our sun.
Wait, what?
These things are whipping around their stars in a matter of days. Their atmospheres are just roasting at thousands of degrees.
But wait, based on that polite model you just mentioned, that shouldn't happen. You can't form a gas giant that close to a star. The gas would just burn off, wouldn't it?
Exactly. You can't form them there, which means they had to have traveled. It suggests this incredibly violent history. These giants likely formed way out, and then through some kind of gravitational chaos, spiraled inward. They migrated.
And a Jupiter-sized planet migrating through a solar system.
It's a wrecking ball. It just clears the board. If there were any little Earths in the way, they got punted into the sun or just ejected out into deep space.
So the fact that we found so many of these tells us a lot of solar systems are violent, chaotic places.
It does. It implies that our solar system, this nice, stable arrangement of circular orbits where the giants stay in the back and the rocks stay in the front, it might actually be the weird one. We might be the boring suburbs in a galaxy of chaotic cities.
That's the first hint that we might be an anomaly. But there was another surprise, right? The super-Earths.
Yes, the super-Earths, which is a really puzzling discovery.
I love the term. It sounds heroic.
It's just a size class. Kepler found that the most common type of planet in the galaxy, at least in its little patch, is a world that's size-wise somewhere between Earth and Neptune. We call them super-Earths or mini-Neptunes.
And we don't have one.
We have 0. We have Earth, which is, 1 Earth radius wide, and then we jump all the way up to Neptune, which is 4 times wider. We're missing the most common planet type in the galaxy.
So again, you look at our home system and ask, why is our architecture so different? Okay, so we have hot Jupiters, we have super-Earths, this whole zoo of exotic worlds. But let's be honest, we aren't really looking for hot Jupiters. We're looking for Earth-like worlds. We want the twin.
We want the mirror image. So astronomers take this massive catalog of thousands of discoveries, and they start applying filters. They become like cosmic bouncers.
Walk me through the velvet rope criteria. What gets you into the Earth-like club?
Okay, so first, you filter by size. You want something rocky. If it's too big, it's just a gas bag. If it's too small, it can't hold onto an atmosphere.
That makes sense.
Second, you filter by location, the Goldilocks zone. It needs to orbit at a distance where liquid water can exist, not ice, not steam.
And the star matters too, I'm guessing. You can't just park next to any old star.
That is a crucial point. You generally want a steady, boring star like our sun. If you orbit a red dwarf, which are super common, you have to get really close to stay warm. But red dwarfs are volatile. They throw out these massive flares. So you might be in the habitable zone for temperature, but you're getting completely irradiated every Tuesday. Not great for life.
Okay, so when we apply all those filters, rocky, habitable zone, sun-like star, what happens to that list of thousands?
It shrinks drastically. I mean, most of the planets we found are too big, too hot, or too cold. But you are left with a handful, maybe a dozen, give or take, depending on how strict you are with the
A
numbers.
dozen candidates?
Out of thousands.
Roughly. And this, right here, this brings us to the core problem of this whole deep dive. It's what we call the knowledge gap.
Because we call them candidates, but that implies we know something about their personality.
And we don't. This is what keeps astrobiologists up at night. We know the box is the right size to hold a pizza. We know the box is at the right temperature to keep the pizza warm.
Okay.
But we have absolutely no idea if there is a pizza inside. It could be empty. It could be full of argon gas. It could be a radioactive wasteland.
We're just seeing shadows and inferring the details. We are seeing silhouettes. We know the radius and we know the orbit. That's pretty much it. We don't know if they have atmospheres. We don't know if they have magnetic fields. We don't know if they have water.
Let's unpack why those missing details are so important, because I think it's easy to gloss over magnetic field as just some sci-fi term. Why is that a deal breaker for life?
It's the shield. Earth has this molten iron core that spins, and it creates a giant magnetic bubble around the planet. That bubble deflects the solar wind, this constant stream of charged particles from the sun.
And without it?
Without it, the sun just strips your atmosphere away bit by bit.
Is that what happened to Mars?
It's the leading theory, yes. Mars is a cautionary tale. It's rocky. It's in the habitable zone, technically. But at some point, its magnetic dynamo died. The shield went down, the atmosphere got blown away into space, and now it's a freeze-dried desert.
So you can have a perfect Earth-sized planet in the habitable zone that is totally dead because its core stopped spinning.
Completely dead, yes.
Okay, so that's one invisible requirement. What about the ground beneath our feet? The sources mention plate tectonics, which feels, I don't know, counterintuitive. Earthquakes are bad for life, right?
Earthquakes are bad for the individual, for sure, but tectonics are essential for the biosphere as a whole. It's the planet's thermostat. Yeah. We have this carbon silicate cycle. Volcanoes pump CO2 out, which keeps us warm.
The greenhouse effect.
Right. But then, weathering of rocks on the surface pulls that CO2 down, cooling us off. Plate tectonics recycles that rock back into the mantle to start the whole process over again.
So it's a giant recycling plant.
It's a climate control system. And if you don't have it, your carbon gets stuck. You either end up in a runaway greenhouse like Venus 900 degrees, crushing pressure, or you freeze over completely. Earth has maintained a temperate climate for billions of years because our surface is moving.
So to really be Earth-like, to be a functional home, you need the size, the temp, the magnetic shield, the recycling crust, the water.
And probably a big moon to stabilize your tilt so your seasons don't go haywire. It's what we call the full package problem.
And we have zero data on whether those dozen candidates have any of those features.
Zero. We are just guessing.
To help us get our heads around this statistical nightmare, there's a great analogy in the research about a neighborhood at night. I want to revisit that because I think it really clarifies this shadow versus reality issue.
Yeah, it's the best way to visualize the data limit we have. So imagine you're in an airplane flying over a massive city at night. You look down, you can see lights. Those are the stars.
Okay.
And every so often you see a tiny shadow pass in front of one of those lights.
The transit method again.
Right. Now, from 30,000 feet, you can measure some things. You can say, okay, that shadow looks to be about 40 feet wide. You can say that shadow is near a bright street lamp. You can infer that it's probably the size of a standard 3-bedroom house.
Okay, so I've identified a house-like shadow.
You have. But here's the catch. You have only ever been inside one house in your entire life. Your own.
Right. And I know my house has a working fridge. I know the plumbing handles hot water. I know the roof doesn't leak.
You have characterized your house, but you're looking down at that shadow 30,000 feet below and you're saying, well, it's the same size as my house, so it must have a working fridge too.
Yeah, that feels like a massive assumption. For all I know, that house is a burnt-out shell. Or it's just a fake movie set propped up by 2x4s.
Precisely. It could be full of toxic mold.
Huh?
But because we have a sample size of 1 hour Earth, we tend to project Earth's qualities onto anything that looks vaguely similar. We assume that rocky plus warm equals life. But scientifically, that is a huge leap of faith, not a data point.
This brings us to the sample size of 1, which is a phrase that usually gets you failed in a statistics class.
Oh, it's terrible statistics. You cannot draw a curve with 1 dot. But Earth is the only dot we have. It's our control group. It's our benchmark. And this leads to really the biggest debate in the field right now, the tension between the optimists and the pessimists.
Lay it out for me. Who are the optimists?
The optimists, they look at the sheer numbers. They say, look, the galaxy has billions of stars. Even if only 1 in a million has that full package, the magnetic field, tectonics, moon, water, that's still thousands of Earths out there.
They're betting on volume.
They're betting on the principle of mediocrity. Earth isn't special. We're just a standard outcome of basic chemistry and physics. If it happened here, it happens everywhere.
Okay. But then you have the rare Earth hypothesis, the pessimists, or maybe the realists.
Right. And they look at the complexity. They say, sure, simple life might be common. Slime could be everywhere. But the very specific chain of events that allowed for complex life, that might be like winning the cosmic lottery a dozen times in a row.
Because maybe you need that Jupiter-sized bodyguard to block asteroids, or you need the moon to keep the tides moving just so.
Exactly. They argue that if you change just one variable, make the sun a little more active, make the crust a little thicker so the plates don't move, the whole experiment fails. They look at Venus and Mars and say, see? Planets die easily. Earth survived.
So, are we a biological factory that the universe just churns out constantly? Or are we a rare jewel in a sea of dead rocks?
And we don't know. We actually can't know until we look inside the other houses.
But that is changing. The source material talks about the next shift in this. We're moving from just finding planets to characterizing them.
This is the really exciting part. We're building the next generation of telescopes, like the Habitable Worlds Observatory.
Yeah.
The goal isn't just to find the shadow anymore. The goal is to collect the light that passes through the atmosphere of that shadow.
We want to sniff the air.
Literally. We want to look for biosignatures, oxygen, methane, water vapor, ozone. If we can analyze the spectrum of light from the atmosphere, we can stop guessing about the fridge and the plumbing. We can see if the lights are on inside.
And that leads to a couple of possible outcomes. And honestly, both of them are kind of mind-bending. I want to play these out. Scenario 1, we turn on the new scope, we point it at those dozen candidates, and we find oxygen everywhere.
That changes human history. Instantly. It means the optimists were right. It means life is a planetary imperative. It means the universe is a garden just teeming with biology. And we are just one leaf on a very, very large tree.
That's the Star Trek future. But what about scenario 2, the lonely road?
We look at the candidates, we analyze the top 100 Earth-like worlds we can find, and we find nothing. Carbon dioxide, nitrogen, dust. We find that they're all either desiccated Mars analogs or steamy Venus twins.
That would mean Earth's temperance, our nice blue, comfortable home, is a fluke.
It would mean we are a statistical anomaly. It would imply that the conditions for complex life are so fragile, so incredibly rare, that we might effectively be alone in this sector of the galaxy.
It's funny, the source makes a point that right now, Earth's rarity is actually based on our ignorance.
Yes, that's the key. The rarity currently lies in our knowledge, not necessarily in the physics. We feel special because we're the only ones we know.
But soon, Earth is going to transition from being the only example to being one point in a distribution.
We will finally get to see the graph. We'll see the curve.
Yeah.
And we will see where we sit on it. Are we in the fat part of the bell curve, totally average? Or are we way out on the tail end, a complete freak occurrence?
It really reframes how you look up at the night sky. You aren't just looking at stars, you're looking at potential answers to the question, is this place a common outcome, or is it a miracle?
And that's the thought to leave this on. Right now, Earth is a paradox. We are simultaneously the most significant place in the universe because we're the only place we know is observing it, and we're also potentially the most average place imaginable. We just don't know which one it is yet.
We are waiting to see if we're a standard model or a custom build.
And until we get that data, Until we can look inside those other houses, we have to treat this planet like it's the only lifeboat in the entire fleet, because for all we know, it is.
That covers 2. Ready for the next one? Let's head to fact 1.
We have finally reached it. The most magnificent revelation on our list. Fact number 1.
It feels like a genuine arrival, doesn't it? We spent this entire series, this extraordinary journey, climbing up this massive mountain of information.
And we are finally at the summit.
I really are.
And looking back at the trail we blazed to get here.
Yeah.
I mean, it's been wild. We started with the solar sweet spot, that perfect Goldilocks zone.
Right.
Then the magnetic shield protecting us, the recycling of the crust through plate tectonics. It's been a lot of geology, a lot of, physics.
And if you step back and look at those previous 9 facts, they all sort of share a specific DNA. They're all about habitability.
The hardware specs.
Exactly, the hardware. How do you build a machine that can keep water liquid? How do you keep an atmosphere from blowing away? It's all stage setting.
But fact number 1, this isn't about the stage anymore, is it?
No. Fact number 1 is a fundamental phase shift. We are moving from discussing the potential for life, the habitability, to discussing awareness. It's not just about a planet existing, it's about the universe waking up.
Okay, so let's define the mission for this final deep dive. What are we actually unpacking here?
Our mission is to grapple with a concept that sounds simple on the surface, but it gets more disorienting the longer you look at it.
Which is?
The concept is that Earth is the only known planet anywhere hosting scientific observers. We need to understand what that means, not just for us, but for the cosmos itself.
The only known planet with scientific observers. When you phrase it like that, it stops being a statistic. It starts feeling, well, heavy.
It should feel heavy.
Lonely, even.
It's a massive statement. It changes the texture of reality.
To really get why that matters, though, I think we need to establish the scale of the silence first.
Absolutely.
Because the universe is a vague term. We throw it around a lot. We need to visualize the canvas we're painting on.
Okay, so let's look at the observable universe. We are talking about a sphere roughly 93 billion light years in diameter.
93 billion.
And inside that sphere, current estimates suggest there are perhaps 2 trillion galaxies.
2 trillion. I can't even hold that number in my head. It's just static.
It's abstract, right? Think of it this way. If you hold a single grain of sand at arm's length against the night sky, a dog sees a sandwich, sure. A bacteria senses a chemical gradient. That is life interacting with its environment for survival. It's biological processing.
Scientific observation is different.
It's not just seeing, it's interrogating. It's looking at the structure of reality and decoding the laws that run it. It is an intentional act of understanding.
So let's visualize that. If we zoom in on this one location, Earth, what does that actually look like in practice?
Well, picture the control room at Caltech right now. You have scientists analyzing data streams coming in from, say, the Voyager probes or the Mars rovers.
They're not just looking at pretty pictures.
No, they're measuring magnetic flux, atmospheric composition, geological history. They're asking, what is this made of?
Or jump over to Switzerland, to CERN. You've got the Large Hadron Collider.
Exactly. This massive 27-kilometer ring buried underground.
And what are we doing there? We're smashing protons together at near light speed just to see what falls out?
We are ripping apart the fabric of matter just to see how it's woven.
That seems like a pretty significant step up from a dog watching a sandwich.
It certainly is. And don't forget the observatories atop Mauna Kea in Hawaii. You have giant mirrors collecting photons, tiny packets of light.
That have been traveling for billions of years.
Billions of years, yeah, since the dawn of time.
It's wild when you frame it that way. We catch these ancient particles, these little messengers, and we use them to build a map of where they came from.
And that is the profundity. I mean, think about what a human being actually is. We are made of carbon, nitrogen, oxygen. We are stardust, quite literally.
Just organized in a really complex way.
Into a complex nervous system. So when those scientists look through the telescope...
It's the universe looking in a mirror.
It is. It's matter examining itself. A rock doesn't ask, why do I fall? A tree doesn't calculate the efficiency of photosynthesis. But we do.
We build the tools.
We build the tools to ask, how did this begin? And how will it end?
And we've even extended that reach physically. You mentioned Voyager 1 earlier.
The little probe that could. It's out there right now in interstellar space. It's escaped the sun's magnetic bubble.
And it's carrying that golden record.
Yeah, greetings in 55 languages, the sound of rain, the brainwaves of a woman falling in love. It's a bottle cast into the cosmic ocean.
It is a physical extension of our awareness, reaching out into the dark.
We are this tiny, tiny speck, but we are the only speck we know of that is looking back at the rest of it.
Unpacking this idea of looking back brings us to an analogy from the source material that I absolutely love.
The library.
The universe as a library.
Yes. This is, I think, the best way to understand the timeline, because the spatial scale is huge, but the time scale is just as overwhelming.
So walk us through this. The universe is the library.
Imagine an incomprehensibly vast library. The shelves go on forever, and the books in this library are written in a very specific language, the language of physics.
The laws of nature.
Exactly. The stories have been there for 13.8 billion years. Stars forming, galaxies colliding, supernovae exploding. These are the dramatic arcs of the cosmos.
The equations were all working.
Perfectly. Gravity worked, fusion worked, chemistry worked, but...
The library was empty.
Precisely. For billions and billions of years, the stories existed, but no one was reading them. The library was silent.
And that's where we come in.
We are the first librarians, or at least the first ones we know of. Humans are like the first entities to walk into this ancient, dusty library and finally learn to read the language.
And we've been reading fast.
Incredibly fast. I mean, think about what we've decoded in just the last few centuries. We've read the book on DNA, on thermodynamics. We've managed to calculate the age of the library itself.
It really puts the extraordinary in the extraordinary 10 when you look at the timeline, though. We haven't been here long.
No. If you compress the history of the universe into a single calendar year, where the Big Bang is January 1st, recorded human history is the last few seconds of December 31st.
The source material gave a specific percentage, I think.
It is only in the last 0.00003% of cosmic history that observers appeared who could comprehend the narrative.
0.00003%. That is a vanishingly small number.
It's a blink. Before that blink, the universe was just happening. Blindly. Mechanically.
And now?
Now it's being understood. We are the characters in the book who have figured out how to read the chapter about our own emergence.
That is the aha moment. We aren't just in the story, we are analyzing the story from the inside.
That gives me chills. We are the universe reading its own diary.
But this naturally and somewhat uncomfortably leads to the biggest question of them all. If we are the librarians, surely we aren't the only staff working here.
The big question, are we alone?
This brings us to the Fermi paradox. I feel like most people have heard the term, but let's define it clearly in this context.
Okay, so the Fermi paradox highlights the tension between two things: expectation and observation.
What we think should be there versus what we see.
Exactly. We look at the galaxy and we know it is ancient, 10, 13 billion years old. We know it is vast, hundreds of billions of stars. Many of those stars have planets.
So logic suggests that if nature does this, creates observers, it should do it often.
Right. If you have a kitchen that bakes cookies and you run the oven for a billion years, you expect more than one cookie.
Exactly. So if technological civilizations are a natural outcome, they should be common.
Yeah.
And some should be millions of years ahead of us.
We should see their engineering. We should hear their radio signals.
But we don't. We call it the Great Silence.
And it is silent. We have radio searches, optical SETI looking for laser pulses. We've analyzed the heat signatures of millions of stars.
Oh, man.
And we have found no unambiguous technosignatures, nothing that screams we are here, just background noise.
That is deeply unsettling. So what are the options? Why is the library so quiet?
Well, the source material lays out the uncomfortable possibilities, and none of them are particularly comforting, but they are all fascinating.
Okay, hit me with them. Possibility number one.
We are the first.
Someone has to be, right?
Exactly. In a 13.8 billion-year-old universe, someone has to be the first to wake up. It could be us. We might be the elder race.
That's a heavy crown to wear. It means there's no one to help us. What's number two?
The filter. This is the darker one. It suggests that technological civilizations might be common, but they are short-lived.
Self-destruction.
Precisely. It suggests there is some barrier, some great filter that stops civilizations from reaching the stars. Maybe when you discover nuclear power or AI, you inevitably destroy yourself.
Like giving a toddler a hand grenade.
And pulling the pin. The silence exists because everyone who learns to speak eventually screams and then dies out.
Okay, that's terrifying. Let's hope it's not that one. What else?
The rarity of intelligence. Life started quickly on Earth, basically as soon as it cooled down. But observers, complex tool-using intelligence, That took 3.7 billion years.
Right. It's one thing to have slime. It's another thing to have a radio telescope.
It's a huge leap. We needed the extinction of the dinosaurs to clear the way for mammals. It's a fragile chain. Maybe most planets get the slime, but the chain of events to get to the scientist almost never happens.
And the last possibility.
Distance. Observers exist. The library has other librarians, but the aisles are just too long.
So we just haven't connected yet.
The gaps between stars are just too vast. It's like two people alone on opposite sides of the Pacific Ocean waving at each other with flashlights. We've only been listening for, what, 60 years?
Not even a blink.
We haven't even cleared our throats yet.
But here's the thing. The source material makes a point that I think cuts through this speculation. Regardless of which answer is right, there is one absolute certainty.
Yes. The universe can produce observers. We are the proof.
It happened here.
It happened here through natural processes. Physics, chemistry, evolution, time. There was no magic involved, just a very, very long road.
So if it happened here, it's physically possible. The machinery of the universe allows for self-reflection.
And that brings us to the most critical pivot of this entire series.
So what? Why does fact number 1 matter to us?
It changes everything about how we view our responsibility. It shifts our identity. We aren't just residents, are we?
We're more than that.
We are the custodians of consciousness.
Custodians of consciousness. That sounds massive.
It is. Think about the stakes. We usually worry about things like nuclear war or climate catastrophe because they would be bad for us.
For our survival, yeah.
But zoom out. If we wipe ourselves out, the consequence isn't just the end of a species of hairless apes. It could mean eliminating the only pair of eyes the universe has for millions of light years.
The universe goes blind again.
In this sector, yes. The library goes dark. No one is left to read the books. The knowledge of the Big Bang, the understanding of DNA, the appreciation of a sunset, it all vanishes with us.
Entropy wins.
The universe goes back to being dumb matter, churning endlessly without meaning.
That puts a very different spin on things like global peace. It's not just about survival. It's about maintaining the capacity to understand. We are holding a torch in a very dark room.
And that torch is heavy. But there is a flip side to the burden. It's not just about the danger, it's about the potential.
The upside.
If we survive, if we mature as a species and spread to other worlds, we propagate the universe's capacity to understand itself.
We become the Johnny Appleseeds of consciousness.
I love that image, yes. There's that famous sentiment from Carl Sagan that we're a way for the cosmos to know itself.
It's not just poetry.
It's a literal. From the Big Bang to general relativity, Earth's observers have mapped the history of everything.
And if we spread, we ensure that the map isn't lost.
Exactly. We could fill the library. We could ensure that the universe never goes blind again.
It really makes you realize that fact number 1 isn't something we found, it's something we are.
That's the beauty of it. The other 9 facts were about the Earth, the crust, the core, the air. This fact is about us and our relationship with everything else. It closes the loop.
So as we wrap up this list, what is the final thought you want to leave our listener with? This one feels like it needs a special sign-off.
I think the most provocative thought is this. Whether we are unique or one of billions, Earth remains the only place we know where the universe has opened its eyes.
The only known location.
We can speculate all day, but we don't know. And until that day comes, we have to act as if we are the only ones. We have to treat this awareness, this ability to understand, as the precious, rare jewel that it is.
Because if we drop it, there might be no one else to pick it up.
Exactly. It's in our hands.
Wow. Okay. That is a lot to process, but in the best way possible. It gives you a reason to get out of bed in the morning, doesn't it?
Just remember to look up.
This has been the Extraordinary 10. We have counted down from the solar sweet spot all the way to the awakening of the universe itself.
It's been quite a ride. I've enjoyed every minute of it.
I want to thank every single one of you who has stuck with us through this entire journey. It's been a blast unpacking these facts with you.
Absolutely.
Make sure you subscribe so you don't miss our next deep dive, where we'll be starting a whole new topic, something a little more down to earth, literally. But for now, for the final time on this countdown, thanks for listening to the Extraordinary 10 podcast.